The night sky has always been a canvas for questions about who we are, where we come from, and what lies beyond the stars. But what if I told you that the universe isn't just expanding outward like a balloon? What if it's stretching, warping, and reshaping itself in ways that challenge everything we think we know about space, time, and reality itself? Today, we're diving into one of the most profound mysteries of the cosmos. Why does the cosmic fabric stretch? And not just stretch, but stretch in ways that seem to defy the very laws we've built our understanding upon. From the invisible force of dark energy to the mind-bending possibilities of quantum fluctuations, we'll explore 15 theories that push the boundaries of science and imagination. Each one offers a unique lens through which to view this cosmic phenomenon, inviting us to rethink not just the universe but our place within it. So, if you've ever looked up at the stars and felt that tug of curiosity, that desire to understand the unfathomable, you're in the right place. This isn't just a journey through space, it's a journey into the unknown, where every answer leads to even more questions. Let's begin. At the heart of our cosmic story lies an event so monumental that it shaped everything we see and everything we count the Big Bang. Picture this, nearly 14 billion years ago, the universe wasn't just smaller or denser, it was everything. All the matter, energy, and space we know today were compressed into a single, unimaginably hot point. Then, in a fraction of a second, something extraordinary happened. The universe erupted into existence, not just expanding, but exploding outward with such force that it set the stage for everything that followed. This wasn't just the birth of stars and galaxies, it was the birth of expansion itself. But here's where things get truly fascinating. The Big Bang didn't just create the universe, it set it in motion. Think of it like a cosmic spring uncoiling with incredible speed. In those first moments, a phenomenon called inflation took hold, stretching space faster than the speed of light. This wasn't just expansion, it was hyper-expansion, a period so brief yet so powerful that it shaped the very structure of the cosmos. And while inflation eventually slowed, the universe never stopped stretching. It's as if the Big Bang imprinted a kind of memory into the fabric of space itself, a lingering momentum that continues to push galaxies apart even today. What's even more intriguing is that this expansion isn't slowing down, it's speeding up. Imagine throwing a ball into the air, only to watch it accelerate upward instead of falling back down. That's the puzzle we're left with. Why does the universe seem to stretch faster and faster? Some scientists point to dark energy, an invisible force that permeates space and drives this acceleration. Others suggest that the answers might lie in the very nature of spacetime itself, a fabric that's far more dynamic and mysterious than we've ever imagined. The Big Bang may have been the spark, but the story of cosmic expansion is far from over. It's a tale that begins with a single explosive moment and unfolds into a universe that's constantly reshaping itself, challenging our understanding of space, time, and the forces that govern them. And as we move forward, this foundation will help us explore the many theories that attempt to explain why the cosmic fabric stretches and what it means for the future of our universe. Now, let's turn our attention to one of the most perplexing and powerful players in this cosmic drama, dark energy. Imagine a force so subtle that we can't see it, touch it, or even detect it directly, yet it's everywhere, shaping the very fabric of the universe. This mysterious entity makes up nearly 70% of the universe's total energy content, dwarfing everything else we know. Stars, planets, galaxies, all of it is just a tiny fraction compared to the overwhelming influence of dark energy. But what exactly is it, and how does it drive the universe to stretch faster and faster? The story of dark energy begins with a surprising discovery in the late 1990s. Astronomers studying distant supernova exploding stars expected to find that the universe's expansion was slowing down, pulled back by gravity over time. But what they found was the opposite. The universe wasn't just expanding, it was accelerating. This was like discovering that a car rolling uphill wasn't slowing down but speeding up without anyone pressing the gas pedal. Something had to be pushing it, and that something was dark energy. So, what could this invisible force be? One leading theory suggests that dark energy is a property of space itself. Think of empty space not as a void, but as a dynamic, living entity. According to this idea, even in the absence of matter or energy, space contains a kind of intrinsic energy, often called vacuum energy or the cosmological constant. This energy exerts a kind of pressure, pushing galaxies apart and stretching the cosmic fabric. It's a bit like trying to inflate a balloon that never stops growing, no matter how much air you add. But dark energy isn't just a theoretical concept, it's supported by multiple lines of evidence. Measurements of the cosmic microwave background, the faint afterglow of the Big Bang, reveal patterns that align with the presence of dark energy. Observations of large-scale structures in the universe, like galaxy clusters, also point to its influence. Yet, despite the mounting evidence, dark energy remains shrouded in mystery. We don't know where it comes from, why it exists, or even if it's truly constant. Could it change over time? Could it one day vanish or grow stronger? These are questions that keep scientists awake at night. And then there's the ultimate question: what does dark energy mean for the fate of the universe? If it continues to drive acceleration, the cosmos could face a cold, dark future. Galaxies would drift apart, stars would fade, and the universe would stretch into an endless, silent void. But if dark energy behaves differently than we think, the outcome could be far more dramatic or even unpredictable. It's a reminder that the universe is full of surprises, and dark energy is one of its greatest enigmas. As we explore the mysteries of dark energy, we're not just uncovering the secrets of the cosmos, we're also confronting the limits of our understanding. This invisible force challenges us to rethink everything we know about space, time, and the nature of reality. And while we may not have all the answers yet, one thing is certain: dark energy is a key piece of the puzzle, a force that shapes the universe in ways we're only beginning to comprehend. Now, let's take a step back in time to uncover one of the most fascinating twists in the history of science: the story of the cosmological constant. It all begins with Albert Einstein, a name synonymous with genius, but even the greatest minds can stumble, or so it seemed. In the early 20th century, Einstein was grappling with a puzzle that seemed to defy his groundbreaking theory of general relativity. According to his equations, the universe should either be expanding or contracting, but the prevailing belief at the time was that the cosmos was static, unchanging, and eternal. To reconcile this, Einstein introduced a mathematical fudge factor, a term he called the cosmological constant. Its purpose: to act as a kind of counterbalance, a repulsive force that would keep the universe from collapsing under its own gravity. At first, the cosmological constant seemed like a clever fix, but it didn't take long for Einstein to regret it. When Edwin Hubble's observations in the late 1920s revealed that the universe was, in fact, expanding, Einstein famously called the cosmological constant his greatest blunder. He discarded it, believing it unnecessary. Yet, as with many ideas in science, the story didn't end there. Decades later, this so-called blunder would make a dramatic comeback, reshaping our understanding of the cosmos in ways Einstein could never have imagined. Fast forward to the late 1990s, when astronomers made a startling discovery. The universe wasn't just expanding, it was accelerating. This revelation turned everything on its head. Suddenly, the cosmological constant wasn't just a theoretical curiosity, it was a crucial piece of the puzzle. Scientists realized that this term, which Einstein had dismissed, could explain the mysterious force driving the universe's accelerated expansion. That force, dark energy, in a twist of cosmic irony, Einstein's greatest blunder, became one of modern cosmology's greatest triumphs. But what exactly is the cosmological constant, and how does it connect to dark energy? At its core, the cosmological constant represents a kind of energy inherent to space itself, a property of the vacuum that fills the universe. Unlike gravity, which pulls things together, this energy exerts a repulsive force pushing galaxies apart. It's as if space itself has a built-in tension, a stretching effect that grows stronger as the universe expands. This idea aligns closely with the concept of dark energy, the mysterious force we explored earlier. In fact, many scientists now see the cosmological constant as the simplest and most elegant explanation for dark energy's effects. Yet, as with all great scientific ideas, the cosmological constant isn't without its challenges. For one, its value is incredibly small, so small that it's difficult to explain why it doesn't cancel itself out. Some physicists argue that this fine-tuning suggests there's more to the story, that the cosmological constant might not be constant after all. Could it change over time? Could it interact with other forces in ways we haven't yet discovered? These questions remain at the forefront of cosmological research, keeping the debate alive and the mystery unsolved. What's truly remarkable about the cosmological constant is how it embodies the spirit of scientific discovery. An idea once cast aside has become a cornerstone of our understanding of the universe. It reminds us that even the greatest minds can't always predict how their work will shape the future, and it challenges us to keep questioning, keep exploring, and keep pushing the boundaries of what we think we know. After all, the universe is full of surprises, and the cosmological constant is proof that sometimes the answers we seek are hidden in the most unexpected places. Let's zoom in now way into a realm so small and strange that it defies our everyday intuition. We're entering the quantum world, where particles flicker in and out of existence like cosmic fireflies, and the rules of physics take on a surreal, almost dreamlike quality. This is the domain of quantum fluctuations, phenomena so tiny they're almost imperceptible, yet their influence stretches across the entire universe. These fluctuations, born in the chaotic swirl of the quantum vacuum, might hold the key to understanding not just the structure of the cosmos, but also the very stretching of its fabric. To grasp the idea of quantum fluctuations, picture the vacuum of space. It's not empty, not in the way we usually think. Instead, it's a seething, bubbling sea of energy where particles and antiparticles spontaneously appear and vanish in the blink of an eye. These fleeting disturbances are called quantum fluctuations, and they're a fundamental feature of the universe at its smallest scales. But here's the remarkable part: these tiny ripples, amplified during the universe's earliest moments, may have sown the seeds for the vast cosmic structures we see today: galaxies, clusters, and the intricate web of matter that spans the cosmos. Now let's connect the dots to the stretching of the cosmic fabric. During the period of cosmic inflation, that hyper-expansion we discussed earlier, quantum fluctuations weren't just tiny blips, they were stretched and magnified to enormous scales. Imagine dipping your fingers into a still pond and creating ripples, then suddenly stretching the pond to the size of an ocean. Those ripples would grow, becoming vast waves that shape the entire surface. In a similar way, quantum fluctuations in the early universe were stretched by inflation, leaving an imprint on the distribution of matter and energy. These imprints are still visible today, etched into the cosmic microwave background like fingerprints from the dawn of time. But could these quantum fluctuations also influence the ongoing expansion of the universe? Some scientists think so. One intriguing possibility is that quantum effects might contribute to the behavior of dark energy, the mysterious force driving the universe's accelerated expansion. If the vacuum of space is filled with these fluctuations, could their energy somehow interact with the fabric of spacetime, causing it to stretch in ways we don't yet fully understand? It's a tantalizing idea, one that bridges the gap between the smallest scales of quantum mechanics and the largest scales of cosmology. Of course, this is still an area of active research, and many questions remain. How exactly do quantum fluctuations translate into the large-scale structure of the universe? Could they hold clues about the nature of dark energy or the ultimate fate of the cosmos? These are the kinds of questions that keep physicists and cosmologists up at night, pushing the boundaries of our knowledge and challenging us to rethink the very nature of reality. What's truly awe-inspiring about quantum fluctuations is how they remind us of the interconnectedness of the universe. From the tiniest particles flickering in the void to the vast expanse of galaxies racing apart, everything is linked by the same underlying principles. It's a humbling thought, one that invites us to marvel at the elegance and complexity of the cosmos. And as we continue to explore these quantum ripples and their cosmic consequences, we're not just uncovering the secrets of the universe, we're also uncovering the deep, hidden threads that weave it all together. Now, let's dive into one of the most revolutionary ideas in modern cosmology, inflation theory. Imagine the universe in its infancy, a fraction of a second old, and already undergoing a transformation so rapid, so immense that it defies comprehension. This isn't just expansion, it's a cosmic growth spurt, an exponential surge that stretched the fabric of space faster than the speed of light. In the blink of an eye, the universe swelled from something smaller than an atom to a size larger than our entire observable cosmos today. But why does this matter, and how does it help us understand the stretching of the cosmic fabric? Inflation theory was first proposed in the early 1980s as a solution to some of the Big Bang's biggest puzzles. One of these puzzles is the so-called horizon problem. Picture the universe as it appears today, remarkably uniform, with the same temperature and density in all directions, even in regions so far apart that light hasn't had enough time to travel between them since the Big Bang. How did these distant regions come to be so similar? Inflation provides an elegant answer. By stretching space faster than light could travel, it smoothed out the universe, making it uniform on the largest scales. But inflation doesn't just explain uniformity, it also sheds light on the origins of cosmic structure. Remember those quantum fluctuations we discussed earlier? Inflation took these tiny ripples in the quantum fabric and stretched them to cosmic proportions. These stretched fluctuations became the seeds for everything we see today: galaxies, clusters, and the vast cosmic web. Without inflation, the universe might have remained a featureless void, devoid of the rich tapestry of matter and energy that fills it now. The evidence for inflation is compelling, but it's not without controversy. One of the strongest pieces of support comes from the cosmic microwave background, the faint afterglow of the Big Bang. Measurements of this radiation reveal tiny temperature variations that align perfectly with predictions made by inflation theory. These variations are like cosmic fingerprints imprinted on the universe during its rapid expansion. Yet, despite this alignment, some scientists argue that inflation is too flexible, that it can explain almost any observation without making specific, testable predictions. This has led to heated debates within the scientific community, with some calling for alternative theories to explain the early universe. One of the most intriguing aspects of inflation is its connection to the ongoing expansion of the universe. While inflation itself lasted only a fraction of a second, its effects are still felt today. The stretching of space during inflation set the stage for the universe's continued growth, creating the conditions for dark energy to take over billions of years later. In a way, inflation was the universe's first great stretch, a prelude to the cosmic expansion we observe now. But what if inflation isn't the whole story? Some theorists propose that inflation might have happened multiple times, creating a multiverse of bubble universes, each with its own unique properties. Others suggest that inflation could be part of a larger cycle, with the universe undergoing periods of expansion and contraction over unimaginably long timescales. These ideas push the boundaries of our understanding, challenging us to think beyond the limits of what we currently know. Inflation theory is more than just a scientific idea. It's a window into the earliest moments of the universe, a glimpse of the forces that shaped the cosmos and continue to shape it today. It reminds us that the universe is a dynamic, ever-changing place, full of surprises and mysteries waiting to be uncovered. And as we continue to explore the implications of inflation, we're not just learning about the past, we're also gaining insight into the future of the cosmos and our place within it. What if the universe we see, the stars, galaxies, and cosmic web stretching endlessly into the void, isn't the whole story? What if it's just one thread in an unimaginably vast tapestry, a single bubble in an ocean of universes? This is the heart of the Multiverse Hypothesis, a bold and speculative idea that takes the concept of cosmic stretching to a whole new level. If true, it would mean that our universe is just one of countless others, each with its own unique laws of physics, its own history, and perhaps even its own version of expansion. But how could such a multiverse influence the stretching of our cosmic fabric? And what would it mean for our understanding of reality? At its core, the Multiverse Hypothesis suggests that our universe might be part of a larger, more complex structure, a cosmic neighborhood where universes are constantly being born, stretching, and interacting. One of the most intriguing versions of this idea comes from inflation theory. Remember how inflation stretched our universe faster than the speed of light? Well, some scientists propose that this rapid expansion didn't happen just once. It could have happened countless times in countless regions of space, giving rise to an infinite number of universes. In this scenario, each universe is like a bubble in a vast cosmic foam, expanding and evolving on its own. But here's where it gets even more fascinating. These universes might not exist in isolation. Some theories suggest that they could collide or interact, leaving subtle imprints on each other's cosmic fabric. Imagine two soap bubbles gently touching. Where they meet, there's a ripple, a disturbance that spreads outward. Could such interactions between universes influence the way our own universe stretches? Some researchers think so. They propose that these collisions might leave behind detectable signatures, like faint patterns in the cosmic microwave background or anomalies in the distribution of galaxies. These clues, though elusive, could hint at a reality far larger and more complex than we've ever imagined. The Multiverse Hypothesis also raises profound questions about the nature of expansion itself. If other universes exist, do they expand in the same way ours does? Or could they follow entirely different rules driven by forces we've never encountered? Some theories suggest that the behavior of dark energy, the mysterious force accelerating our universe's expansion, might be influenced by interactions with other universes. It's as if the cosmic fabric isn't just stretching within our universe, but is part of a larger, interconnected system, where the boundaries between worlds blur and the forces that shape them intertwine. Of course, the multiverse remains a highly speculative idea, and not all scientists are convinced. Critics argue that it's difficult, if not impossible, to test experimentally. After all, how do you observe something that lies beyond the boundaries of our observable universe? Yet, despite these challenges, the Multiverse Hypothesis continues to captivate the imagination of physicists and cosmologists. It pushes the boundaries of what we consider possible, challenging us to think beyond the limits of our own universe and explore the infinite possibilities that might lie beyond. What makes the multiverse hypothesis so compelling isn't just its scientific implications, it's the way it reshapes our perspective. If our universe is just one of many, then the questions we ask about its origins, its structure, and its future take on a new dimension. Are we alone in this grand cosmic tapestry, or are there other universes out there, each with its own story to tell? And if so, what does that mean for our place in the cosmos? These are questions that stretch not just the fabric of space, but the limits of our curiosity and imagination. As we ponder the multiverse, we're reminded that the universe, or universes, are far stranger and more wondrous than we can fully comprehend. It's a humbling thought, one that invites us to keep exploring, keep questioning, and keep pushing the boundaries of what we think we know. After all, the cosmos is full of surprises, and the multiverse might just be the greatest one of all. What if everything we see, stars, planets, galaxies, even space itself, is made up of something far smaller and more fundamental than particles? What if the universe at its deepest level is composed of tiny, vibrating strings? This is the bold claim of string theory, one of the most ambitious and imaginative ideas in modern physics. It suggests that the fabric of reality isn't woven from point-like particles, but from one-dimensional strings, each vibrating at different frequencies to create the rich tapestry of the cosmos. And here's where it gets even more intriguing. These vibrations might not just shape matter and energy, they could also influence the very stretching of the cosmic fabric. To understand string theory, let's start with the basics. In traditional physics, particles like electrons and quarks are seen as the smallest building blocks of the universe. But string theory proposes a radical shift. Instead of particles, imagine tiny, looped strings, each one so small that if an atom were the size of our solar system, a string would be no bigger than a tree on Earth. These strings aren't static, they vibrate, oscillating at different frequencies like the strings of a cosmic guitar. And just as the pitch of a guitar string depends on how it vibrates, the properties of particles, their mass, charge, and even the forces they experience are determined by the vibrations of these fundamental strings. But how does this connect to the expansion of the universe? According to string theory, the vibrations of these strings don't just create particles, they also interact with the fabric of spacetime itself. Imagine spacetime as a giant cosmic drumhead, and these strings as tiny drumsticks tapping out rhythms that ripple through the universe. These ripples could influence how space stretches and evolves, potentially playing a role in the mysterious acceleration driven by dark energy. It's as if the universe isn't just expanding, it's resonating, vibrating in harmony with the strings that make it up. One of the most exciting aspects of string theory is its potential to unify physics. For decades, scientists have struggled to reconcile two of the most successful but seemingly incompatible theories: general relativity, which describes the large-scale structure of the universe, and quantum mechanics, which governs the behavior of particles at the smallest scales. String theory offers a tantalizing solution. By describing everything from the tiniest particles to the largest galaxies as vibrations of strings, it could provide a single framework that bridges the gap between these two worlds. This unification could help us understand not just how the cosmos stretches, but why it stretches in the way it does. Of course, string theory isn't without its challenges. For one, it requires extra dimensions, up to 10 or even 11 beyond the 3 dimensions of space and 1 of time that we experience. These extra dimensions are thought to be curled up so tightly that they're invisible to us, but their existence is crucial for the math to work. While this might sound like science fiction, it's a serious idea that's backed by complex equations and decades of research. Yet, because these dimensions are so hard to detect, string theory remains largely untested, leaving some scientists skeptical about its validity. Despite these uncertainties, string theory continues to inspire and challenge physicists. It pushes us to think beyond the limits of traditional physics, offering a vision of the universe that's as beautiful as it is complex. And while we may not yet have the tools to prove or disprove it, the very idea of a universe woven from vibrating strings invites us to see the cosmos in a new light, not just as a collection of objects, but as a symphony of vibrations resonating through the fabric of reality. As we explore the implications of string theory, we're reminded that the universe is far more intricate and interconnected than we often realize. It's a reminder that even the smallest details, like the vibrations of a string, can have profound consequences for the largest scales, shaping the very structure and evolution of the cosmos. And as we continue to unravel these mysteries, we're not just learning about the universe, we're also discovering new ways to listen to its music, to hear the rhythms and harmonies that echo through the cosmic fabric. Imagine our universe as a sheet of paper, floating in a vast, higher-dimensional space, a space so strange and complex that it defies our everyday understanding of reality. This is the essence of brain cosmology, a theory that takes the idea of the multiverse to an entirely new level. According to this concept, our universe isn't just one of many possible universes. It's a membrane or brain, drifting in a higher dimensional realm called the bulk. These brains aren't static. They can move, collide, and interact, potentially sparking events as monumental as the Big Bang itself. But how does this relate to the stretching of the cosmic fabric, and what could it mean for the future of our universe? The story of brain cosmology begins with string theory, which we explored earlier. In string theory, the fundamental building blocks of reality aren't particles but tiny, vibrating strings. To make the math work, the theory requires extra dimensions, up to 10 or 11 beyond the 3 spatial dimensions and 1 time dimension we experience. Brain cosmology takes this idea a step further, suggesting that our universe is a 3-dimensional brain embedded in these higher dimensions. Think of it like a slice of bread in a cosmic loaf, a single layer in a much larger, multidimensional structure. But what makes brains so fascinating is their potential for interaction. In this higher dimensional space, brains can move, collide, and even merge. Some scientists propose that such a collision could have been the catalyst for the Big Bang, setting off the explosive expansion that gave rise to our universe. Imagine 2 sheets of paper floating in the air, gently brushing against each other. That contact could release an enormous amount of energy, triggering a cosmic event that reshapes everything around it. In the case of brains, this collision might have ignited the rapid expansion of space itself, leaving behind the cosmic microwave background as a faint echo of that primordial moment. This idea isn't just speculative, it has real implications for how we understand the universe's expansion. If brains can collide and trigger expansion, could they also influence the ongoing stretching of the cosmic fabric? Some theories suggest that interactions between brains might contribute to the behavior of dark energy, the mysterious force accelerating the universe's expansion. It's as if the fabric of space isn't just stretching within our brain, but is also being tugged and shaped by the movements of other brains in the higher dimensional bulk. One of the most intriguing aspects of brain cosmology is its potential to explain the fine-tuning of the universe. Why do the laws of physics seem so perfectly calibrated to allow for the existence of stars, planets, and life? If our universe is just one brain among many, each with its own set of physical laws, it's possible that we simply exist in one of the rare brains where conditions are just right. This idea, known as the Anthropic Principle, offers a new perspective on the nature of reality, suggesting that our universe might be one small part of a much larger, more varied multiverse. Of course, brain cosmology isn't without its challenges. For one, higher dimensions are notoriously difficult to detect, and collisions between brains would leave behind subtle, hard-to-find signatures. Scientists are actively searching for evidence, such as gravitational waves or anomalies in the cosmic microwave background, that could hint at these higher dimensional interactions. While no definitive proof has been found yet, the search itself is driving new discoveries and pushing the boundaries of our understanding. What makes brain cosmology so compelling is the way it challenges us to think beyond the limits of our three-dimensional experience. It invites us to imagine a universe or multiverse that's far richer and more complex than we've ever imagined. And as we explore the implications of brains and their potential collisions, we're not just uncovering the secrets of the cosmos, we're also redefining what it means to ask questions about the nature of reality. In the end, brain cosmology reminds us that the universe is full of surprises, and the answers we seek might lie in dimensions we can't yet see. It's a humbling thought, one that inspires awe and curiosity in equal measure. And as we continue to probe the mysteries of brains, collisions, and higher dimensions, we're not just exploring the universe, we're exploring the very edges of what's possible. What if the very foundation of our understanding of gravity is missing something? For over a century, Einstein's theory of general relativity has been the cornerstone of modern physics, describing gravity as the curvature of spacetime caused by mass and energy. It's a theory that has passed every test thrown at it, from predicting the bending of light around massive objects to explaining the precise orbits of planets. But what if, on the grandest scales of the cosmos, this theory isn't the full story? What if the stretching of the universe isn't driven by dark energy, but by a deeper, more nuanced understanding of gravity itself? This is the provocative idea behind modified gravity theories, a bold reimagining of one of science's most cherished frameworks. At the heart of these theories is a simple yet profound question. Could the accelerated expansion of the universe be explained not by an invisible force like dark energy, but by tweaking the laws of gravity? It's a radical proposition, one that challenges the very essence of Einstein's legacy. Modified gravity theories suggest that on cosmic scales, gravity might behave differently than it does in our local neighborhood. Imagine gravity as a rubber band, stretchy and flexible in some places, rigid and unyielding in others. In this view, the universe's expansion might not need dark energy to explain it. Instead, gravity itself could be stretching space in unexpected ways. One of the most well-known modified gravity theories is called modified Newtonian dynamics, or MUND. Proposed in the early 1980s, MUND was originally designed to explain anomalies in the rotation speeds of galaxies without invoking dark matter. But in recent years, some researchers have adapted MUND to address cosmic expansion as well. Instead of dark energy pushing galaxies apart, MUND suggests that gravity weakens more slowly over vast distances than predicted by general relativity. It's as if the rubber band of gravity loses its tension in the far reaches of the cosmos, allowing space to stretch more easily. Another intriguing approach comes from theories like FR gravity, which modify Einstein's equations to include additional terms that become significant on large scales. These theories propose that gravity isn't just about mass curving spacetime, it's also about how spacetime itself evolves over time. In this view, the stretching of the cosmic fabric could be a natural consequence of gravity's modified behavior without the need for dark energy. It's a bit like discovering that the rules of a game you've been playing for years have hidden complexities you never noticed before. But here's the challenge: modified gravity theories must do more than just offer an alternative explanation. They must also match the wealth of observational data we've collected. From the precise measurements of the cosmic microwave background to the detailed mapping of galaxy clusters, any viable theory has to account for all the evidence that currently supports dark energy. So far, no modified gravity theory has fully succeeded in doing this, leading some scientists to remain skeptical. Yet, the search continues, driven by the tantalizing possibility that we might be missing a crucial piece of the puzzle. What makes modified gravity theories so compelling isn't just their potential to explain cosmic expansion, it's the way they challenge us to rethink the very nature of gravity. They remind us that science is a never-ending journey, one where even the most established ideas can be questioned and refined. And as we explore these bold new frameworks, we're not just probing the mysteries of the universe, we're also pushing the boundaries of our own understanding. In the end, whether modified gravity theories hold the key to cosmic expansion or not, they serve as a powerful reminder that the universe is full of surprises. They invite us to keep asking questions, to keep testing our assumptions, and to keep searching for the deeper truths that shape the cosmos. And in that search, we might just uncover a new chapter in the story of gravity, one that reshapes our understanding of the universe and our place within it. Let's shift our focus to something that sounds like a contradiction: the power of empty space. At first glance, the vacuum of space might seem like nothingness, a vast, silent void where nothing happens. But in reality, it's anything but empty. According to quantum mechanics, even the emptiest regions of space are alive with activity, buzzing with a kind of energy that's both invisible and incredibly powerful. This is vacuum energy, a phenomenon that defies our everyday intuition and might hold the key to understanding why the universe stretches the way it does. So, what exactly is vacuum energy? Imagine the vacuum of space as a bubbling cauldron, where particles and their antimatter counterparts constantly pop into existence, only to annihilate each other in an instant. These fleeting disturbances are known as quantum fluctuations, and they're a fundamental feature of the universe at its smallest scales. But here's the twist: even when these particles vanish, they leave behind a kind of residue, a persistent energy that fills the vacuum. This energy isn't just a theoretical curiosity. It's a real, measurable force that could be driving the expansion of the universe. This brings us to the cosmological constant, a concept we've touched on earlier. Remember how Einstein introduced this term to balance his equations, only to later dismiss it as his greatest blunder? Well, vacuum energy offers a compelling explanation for what the cosmological constant might represent. In this view, the constant isn't just a mathematical fudge factor, it's a description of the energy inherent to the vacuum of space itself. This energy exerts a kind of pressure, pushing galaxies apart and stretching the cosmic fabric. It's as if empty space has a built-in tension, a stretching effect that grows stronger as the universe expands. But how does this connect to the accelerating expansion we observe today? One possibility is that vacuum energy is the source of dark energy, the mysterious force driving the universe's accelerated growth. If the vacuum is filled with this intrinsic energy, it could act like a kind of cosmic engine, constantly pushing space outward. Think of it like inflating a balloon that never stops growing no matter how much you stretch it. The energy inside keeps the process going. This idea aligns closely with observations of distant supernova and the cosmic microwave background, both of which suggest that something is causing the universe to expand faster and faster. Of course, vacuum energy isn't without its challenges. For one, its predicted value from quantum field theory is staggeringly large, so large that it would cause the universe to expand at a rate far beyond what we observe. This discrepancy, known as the cosmological constant problem, is one of the biggest unsolved puzzles in modern physics. Why is vacuum energy so much weaker than theory suggests? Could there be some mechanism that cancels out most of its effects, leaving just the tiny amount needed to drive cosmic acceleration? These are questions that continue to baffle scientists, pushing them to explore new ideas and rethink old assumptions. One intriguing possibility is that vacuum energy isn't constant. It could change over time, fluctuating in ways we don't yet understand. If that's the case, the stretching of the cosmic fabric might not be a one-size-fits-all process. Instead, it could vary depending on the energy density of the vacuum, leading to periods of rapid expansion, slow contraction, or even stability. This idea opens up a whole new realm of possibilities for the future of the universe, challenging us to think beyond the simple narrative of endless acceleration. What makes vacuum energy so fascinating isn't just its potential to explain cosmic expansion. It's the way it blurs the line between something and nothing. It reminds us that even the emptiest spaces are teeming with potential, filled with forces and phenomena that shape the very fabric of reality. And as we continue to explore this mysterious energy, we're not just uncovering the secrets of the universe, we're also discovering new ways to understand the profound interplay between emptiness and existence. In the end, vacuum energy isn't just a scientific concept, it's a reminder that even in the void, there's always more to discover. Now, let's journey into one of the most mind-bending ideas in modern physics, a concept so radical it turns our understanding of reality inside out. Imagine the universe not as a three-dimensional expanse filled with stars and galaxies, but as a kind of cosmic hologram, a projection of information encoded on a two-dimensional surface. This is the essence of the holographic principle, a theory that suggests the cosmos we see might be nothing more than a grand illusion, a shadow cast by the true nature of reality. But how does this idea connect to the stretching of the cosmic fabric, and what does it mean for our understanding of space, time, and the very nature of existence? The holographic principle has its roots in the study of black holes, those enigmatic regions of space where gravity is so intense that not even light can escape. In the 1970s, physicist Jacob Bekenstein and later Stephen Hawking discovered something astonishing. The information about everything that falls into a black hole isn't lost forever. Instead, it's somehow encoded on the black hole's event horizon, the boundary beyond which nothing can escape. This idea sparked a revolutionary thought. If information about a three-dimensional object can be stored on a two-dimensional surface, could the same be true for the entire universe? At first glance, the idea seems almost absurd. How could the vast three-dimensional cosmos we inhabit, filled with galaxies, planets, and life, be encoded on a flat, two-dimensional surface? Yet, the mathematics behind the holographic principle is surprisingly robust. It suggests that the universe might operate like a hologram, where every point in three-dimensional space corresponds to information stored on a two-dimensional boundary. Imagine watching a movie projected on a screen. The images appear three-dimensional with depth and movement, but in reality, they're just flat patterns of light. In a similar way, the holographic principle proposes that the universe we experience might be a projection of information stored on a distant, two-dimensional surface. But what does this mean for the stretching of the cosmic fabric? If the universe is a hologram, then the expansion we observe, the galaxies racing apart, the space stretching between them, might be a reflection of changes happening on this two-dimensional surface. It's as if the cosmic projection is being stretched, warped, and reshaped by the underlying information. This idea challenges our traditional view of space and time, suggesting that they might not be fundamental at all, but emergent properties arising from something deeper and more abstract. One of the most fascinating aspects of the holographic principle is its potential to unify two of the most important theories in physics: quantum mechanics and general relativity. Quantum mechanics describes the behavior of particles at the smallest scales, while general relativity explains the large-scale structure of the cosmos. But the two theories have long been at odds, each operating under different rules. The holographic principle offers a tantalizing bridge between them, suggesting that the quantum information encoded on a two-dimensional surface could give rise to the spacetime we experience in three dimensions. It's a vision of the universe where the microscopic and the cosmic are deeply intertwined, connected by the thread of information. Of course, the holographic principle isn't without its challenges. For one, it's incredibly difficult to test experimentally. How do you prove that the universe is a hologram when all our observations are made within it? Some scientists are exploring ways to detect subtle hints of the holographic nature of reality, such as anomalies in the cosmic microwave background or the behavior of gravitational waves. Others are using advanced mathematical models to refine the theory, searching for ways to make it more concrete and testable. While the evidence is still tentative, the idea continues to captivate physicists and cosmologists, pushing the boundaries of what we thought was possible. What makes the holographic principle so compelling isn't just its scientific implications, it's the way it reshapes our perspective on reality. It invites us to see the universe not as a collection of objects in space, but as a vast, interconnected web of information. It challenges us to think beyond the limits of our three-dimensional experience, to imagine a cosmos that's far stranger and more wondrous than we've ever imagined. And as we continue to explore this radical idea, we're not just uncovering the secrets of the universe, we're also discovering new ways to understand the profound interplay between information, space, and time. In the end, the holographic principle reminds us that reality is full of surprises, and the answers we seek might lie in dimensions we can't yet see. It's a humbling thought, one that inspires awe and curiosity in equal measure. And as we continue to probe the mysteries of this cosmic hologram, we're not just exploring the universe, we're exploring the very edges of what it means to exist. Now, let's turn our attention to a pair of cosmic players that might seem unrelated at first glance, but are deeply intertwined in shaping the universe as we know it: dark matter and cosmic inflation. Dark matter, that mysterious, invisible substance that makes up about 27% of the universe, is famous for its gravitational influence. It's the unseen hand that guides the formation of galaxies and holds galaxy clusters together. But could it also play a role in the stretching of the cosmic fabric? And how does it connect to inflation, that explosive period of hyper-expansion in the universe's infancy? The answers might just reveal a dynamic duo working in tandem to shape the cosmos. First, let's revisit dark matter. Unlike ordinary matter, dark matter doesn't emit, absorb, or reflect light, making it invisible to our telescopes, but its presence is undeniable. We see its gravitational effects in the way galaxies rotate and the way light bends around massive objects. It's like the invisible scaffolding of the universe, providing the structure needed for cosmic growth. Now, here's where things get interesting. While dark matter doesn't directly interact with light, it does interact with gravity. And gravity, as we know, is the force that bends and shapes space-time itself. So, if dark matter's gravitational pull is strong enough to hold galaxies together, could it also influence how the universe expands? This is where cosmic inflation comes into play. Remember, inflation was that brief but explosive period just after the Big Bang when the universe expanded faster than the speed of light. It stretched space so dramatically that it smoothed out the cosmos, creating the conditions for galaxies and stars to form billions of years later. But here's the twist: inflation didn't just stretch space, it also amplified tiny quantum fluctuations, seeding the universe with the clumps of matter that would eventually grow into galaxies. And dark matter, with its gravitational pull, played a crucial role in pulling those clumps together, forming the cosmic structures we see today. But could dark matter have influenced inflation itself? Some theories suggest that dark matter might have been present during those early moments, interacting with the inflating universe in ways we're only beginning to understand. Imagine inflation as a cosmic tidal wave, sweeping through the universe and stretching it to unimaginable scales. dark matter, with its gravitational influence, might have acted like an anchor, subtly shaping how that wave spread. It's as if dark matter was working behind the scenes, guiding the expansion and ensuring that the universe grew in a way that allowed galaxies and stars to form. What's even more fascinating is how dark matter and inflation might continue to influence the universe today. While inflation ended billions of years ago, the stretching it started never stopped. Dark energy, as we've discussed, has taken over the job of accelerating the expansion, but dark matter's gravitational pull is still at work, counterbalancing that expansion on smaller scales. It's a delicate cosmic dance. Dark energy stretches the universe outward, while dark matter pulls matter together, creating the intricate web of galaxies and voids we observe. Together, these forces shape the universe's evolution, from its earliest moments to its present-day structure. This interplay between dark matter and inflation raises profound questions about the nature of the cosmos. Could dark matter have left imprints on the cosmic microwave background, the afterglow of the Big Bang? Could its gravitational effects help explain why the universe expanded so uniformly during inflation? These are questions that scientists are actively exploring, using advanced simulations and observations to piece together the story of how these forces shaped the universe. What makes this exploration so compelling is the way it ties together two of the most mysterious and powerful aspects of cosmology. Dark matter and inflation might seem like separate pieces of the puzzle, but together they form a dynamic duo that has shaped the universe from its very beginning. And as we continue to unravel their secrets, we're not just learning about the cosmos, we're discovering how the forces that govern it work in harmony to create the universe we call home. It's a reminder that even in the vastness of space, every force, every particle, and every interaction plays a part in the grand cosmic story. Let's step into a concept that feels almost paradoxical: the idea that disorder might be shaping the very structure of the universe. This is the realm of entropy, a term that often conjures images of chaos and decay. But in the grand scheme of the cosmos, entropy is far more than just a measure of disorder. It's a fundamental force that governs the flow of time and the evolution of everything around us. And here's the twist: as the universe expands, entropy increases. But could this relentless march toward disorder also be driving the stretching of the cosmic fabric itself? To explore this, we'll need to unpack the deep connection between entropy, time, and the expansion of the universe. Entropy is often described as the universe's tendency to move from order to disorder. Think of it like a deck of cards. When you shuffle it, the cards become more random, more disordered. That's entropy in action. But in the cosmos, entropy isn't just about shuffling cards. It's about the way energy spreads out, the way stars burn out, and the way galaxies drift apart. It's a universal trend, one that defines the arrow of time itself. Without entropy, time wouldn't have a direction. We wouldn't have cause and effect, growth and decay, or even the ability to remember the past and anticipate the future. Entropy is what makes time flow forward, but here's where it gets fascinating. As the universe expands, entropy increases. This might seem counterintuitive at first. After all, expansion creates more space, and more space might seem like it could lead to more order, not less. But the opposite is true. As the universe stretches, matter and energy spread out, becoming more diluted and less concentrated. This spreading out is what drives entropy upward. It's like pouring ink into a glass of water. The ink starts out concentrated, but as it spreads, it becomes more disordered, mixing with the water until it's evenly distributed. In the same way, the stretching of the cosmic fabric increases entropy, pushing the universe toward a state of maximum disorder. Now, let's take this a step further. Could entropy itself be influencing the expansion of the universe? Some scientists think so. One intriguing idea is that the increase in entropy might be acting as a kind of cosmic engine, driving the universe to stretch faster and faster. Think of it like this: as entropy rises, it creates a kind of pressure, a push toward greater disorder. This pressure could be contributing to the acceleration we observe in cosmic expansion, working alongside dark energy to stretch the fabric of spacetime. It's as if the universe is not just expanding, it's being pulled apart by the relentless force of entropy. This connection between entropy and expansion raises profound questions about the nature of time and the future of the cosmos. If entropy is driving cosmic stretching, what does that mean for the ultimate fate of the universe? One possibility is that the universe will continue to expand indefinitely, becoming colder, darker, and more disordered until it reaches a state known as the heat death. In this scenario, entropy would reach its maximum, and the universe would become a vast, uniform sea of energy, with no stars, no galaxies, and no life. It's a bleak vision, but it's one that aligns with our current understanding of entropy and cosmic expansion. But not everyone agrees with this view. Some scientists propose alternative scenarios, such as the idea that entropy could eventually trigger a kind of cosmic reset, leading to a new Big Bang and the birth of a new universe. Others suggest that entropy might interact with other forces, like dark energy or quantum fluctuations, in ways we don't yet understand. These ideas challenge us to think beyond the traditional narrative of heat death, opening up new possibilities for the future of the cosmos. What makes entropy so compelling is the way it connects the smallest scales of quantum mechanics to the largest scales of cosmology. It's a reminder that even the most fundamental processes like the flow of time and the expansion of space are deeply intertwined. And as we continue to explore the role of entropy in shaping the universe, we're not just uncovering the secrets of cosmic expansion, we're also gaining new insights into the nature of time, the direction of history, and the ultimate destiny of all things. In the end, entropy isn't just a measure of disorder, it's a force that shapes the very fabric of reality. It's a reminder that the universe is always in motion, always evolving, and always pushing toward something new. And as we ponder the profound interplay between entropy, time, and cosmic expansion, we're reminded that even in the face of disorder, there's a kind of order, a rhythm, a pattern, a story that's still being written. It's a story that invites us to keep exploring, keep questioning, and keep marveling at the incredible complexity of the cosmos. What if the universe isn't on a one-way journey toward endless expansion? What if, instead of stretching forever into a cold, dark void, the cosmos is caught in an eternal dance of expansion and contraction, a cosmic heartbeat pulsing through time and space? This is the essence of the cyclic universe model, a theory that flips the script on our understanding of cosmic evolution. It suggests that the universe isn't just stretching, it's breathing, expanding and contracting in an endless cycle that could redefine everything we think we know about its past, present, and future. The idea of a cyclic universe isn't new. In fact, it echoes ancient philosophical and spiritual traditions that imagine the cosmos as a living, cyclical entity. But in modern cosmology, this concept has taken on a new life, supported by mathematical models and theoretical frameworks that challenge the traditional narrative of a one-time Big Bang followed by endless expansion. At its core, the cyclic universe model proposes that our universe isn't a singular event, it's just one chapter in an infinite series of cosmic cycles, each beginning with expansion and ending with contraction, only to start anew. So how does this cycle work? Let's break it down. Imagine the universe expanding just as we observe today, driven by dark energy and the stretching of spacetime. But instead of continuing forever, this expansion eventually slows, stops, and reverses. Galaxies, once racing apart, begin to drift closer together. Space itself starts to contract, collapsing inward like a deflating balloon. This contraction continues until the universe reaches a state of extreme density and heat, a big crunch, as it's often called. Then, in a moment of cosmic rebirth, this dense, hot state triggers another Big Bang, launching a new cycle of expansion. It's as if the universe is caught in an endless loop, expanding and contracting like the tides of an infinite cosmic ocean. But what could cause this reversal? One possibility lies in the behavior of dark energy. In the cyclic model, dark energy isn't a constant force pushing the universe apart forever. Instead, it could change over time, weakening or even reversing its effects. As dark energy's influence wanes, gravity, the great cosmic pull, could take over, drawing everything back together. This interplay between expansion and contraction creates a delicate balance, one that keeps the universe cycling through its phases without ever reaching a final, static state. The implications of this model are profound. For one, it challenges the idea of a definitive beginning or end to the universe. Instead of a single Big Bang, there could have been countless Big Bangs, each one marking the start of a new cycle. This raises fascinating questions about the nature of time itself. Is time linear as we typically think, or is it cyclical, repeating itself with each new cosmic phase? And if the universe has undergone countless cycles before, what does that mean for the future? Could our current cycle be just one of many with no end in sight? The cyclic universe model also offers a fresh perspective on the idea of entropy, the tendency toward disorder that we explored earlier. In a cyclic universe, entropy doesn't lead to an inevitable heat death. Instead, each cycle resets the cosmic clock, allowing entropy to start anew. It's as if the universe has a built-in mechanism for renewal, a way to refresh itself and begin again. This idea opens up new possibilities for the fate of the cosmos, suggesting that even as entropy increases, the universe might find a way to rebound, creating new structures, new galaxies, and perhaps even new life. Of course, the cyclic universe model isn't without its challenges. For one, there's the question of how each cycle transitions into the next. What triggers the big crunch, and how does it lead to a new Big Bang? Some theories propose that collisions between branes in higher dimensional space could spark these cycles, while others suggest that quantum effects might play a role. But until we find definitive evidence, these ideas remain speculative, inviting further exploration and debate. What makes the cyclic universe model so compelling is the way it reimagines the cosmos as a dynamic, ever-changing entity. It's a vision that challenges us to think beyond the limits of our current understanding, to imagine a universe that's not just expanding but evolving, cycling through phases of growth and renewal. And as we continue to explore this idea, we're reminded that the universe is full of surprises, always ready to reveal new layers of mystery and wonder. In the end, the cyclic universe model invites us to see the cosmos not as a static, one-way journey, but as a living, breathing system full of rhythm and repetition. It's a reminder that even in the vastness of space, there's a kind of order, a pattern that connects the past, present, and future. And as we ponder the possibilities of endless cycles, we're reminded that the universe is always in motion, always changing, and always offering new ways to understand its incredible complexity. It's a story that invites us to keep exploring, keep questioning, and keep marveling at the beauty of the cosmos. Now, let's venture into a realm where the very rules of physics seem to blur, a frontier where the colossal meets the infinitesimal. This is the domain of quantum gravity, a field of science that seeks to unite two of the most powerful but seemingly incompatible theories ever conceived: general relativity, which governs the behavior of massive objects and the fabric of space-time, and quantum mechanics, which describes the bizarre and unpredictable world of particles at the smallest scales. These two theories have revolutionized our understanding of the universe, but they operate under entirely different rules. General relativity paints a smooth, continuous picture of space-time, while quantum mechanics reveals a chaotic, flickering reality at the tiniest levels. So, what happens when we try to bring them together, and how could this unification shed light on the stretching of the cosmic fabric? The quest for quantum gravity is one of the most ambitious challenges in modern physics. At its core, it's about finding a single framework that can explain gravity not just on the scale of planets and galaxies, but also at the level of atoms and particles. This is no small feat. When we try to apply the principles of quantum mechanics to gravity, the math breaks down, producing nonsensical results like infinite energies or probabilities greater than 1. It's as if the universe is telling us that our current tools aren't enough, that we need a new way of thinking, a new language to describe the cosmos. And that's exactly what quantum gravity aims to provide. One of the most promising approaches to quantum gravity is a theory called loop quantum gravity. Unlike string theory, which proposes that the fundamental building blocks of reality are tiny, vibrating strings, loop quantum gravity suggests that spacetime itself is quantized, broken into discrete, indivisible units. Imagine spacetime as a fabric woven from tiny loops, each one representing the smallest possible piece of reality. These loops interact and intertwine, creating the smooth, continuous spacetime we experience on larger scales. But at the smallest levels, spacetime becomes granular, like a digital image made up of individual pixels. This granularity could have profound implications for how we understand cosmic expansion. For instance, if spacetime is made up of these tiny loops, then the stretching of the cosmic fabric might not be as smooth as we think. Instead of a continuous expansion, the universe could be expanding in tiny, discrete steps, like the ticking of a cosmic clock. This idea challenges our traditional view of spacetime as a fluid, unbroken entity and opens up new possibilities for understanding how the universe evolves. Could these quantum steps in spacetime explain the accelerated expansion we observe today? Could they hint at a deeper connection between gravity and the mysterious force of dark energy? These are questions that quantum gravity theorists are actively exploring, pushing the boundaries of our understanding. Another intriguing idea comes from a concept known as quantum foam. This theory suggests that at the smallest scales, spacetime isn't smooth or even granular. It's a chaotic, frothy sea of fluctuations, where tiny regions of space and time pop in and out of existence. It's as if the vacuum of space is alive with activity, constantly bubbling and churning. In this view, the stretching of the cosmic fabric might be influenced by these quantum fluctuations, with spacetime expanding and contracting in unpredictable ways. This could provide a new explanation for the uneven distribution of matter and energy in the universe, or even the mysterious acceleration driven by dark energy. But quantum gravity isn't just about explaining cosmic expansion. It's also about resolving some of the deepest mysteries in physics. For example, what happens at the center of a black hole where gravity becomes infinitely strong and spacetime breaks down? Or what occurred in the first moments of the Big Bang when the universe was unimaginably small and dense? These are questions that general relativity and quantum mechanics can't answer on their own, but quantum gravity could hold the key. By unifying these two theories, we might finally unlock the secrets of these extreme environments, shedding light on the origins and ultimate fate of the cosmos. Of course, quantum gravity is still a work in progress, and many questions remain. How do we test these ideas when the effects of quantum gravity are so tiny and elusive? What experiments could we design to probe the granularity of spacetime or the nature of quantum foam? These challenges are daunting, but they're also exciting, driving scientists to think creatively and push the limits of technology. What makes quantum gravity so compelling is the way it bridges the gap between the very large and the very small, offering a glimpse of a universe that's more interconnected and unified than we've ever imagined. It's a reminder that the cosmos isn't just a collection of separate phenomena. It's a single, dynamic system governed by principles we're still striving to understand. And as we continue to explore this frontier, we're not just uncovering the secrets of gravity or the stretching of space-time. We're discovering new ways to see the universe as a whole, a tapestry woven from the threads of space, time, and energy. In the end, quantum gravity invites us to think beyond the limits of our current theories, to imagine a cosmos where the rules are rewritten and the possibilities are endless. It's a journey that challenges us to keep asking questions, to keep exploring, and to keep marveling at the incredible complexity of the universe. And as we take these steps toward a deeper understanding, we're reminded that the cosmos is full of surprises, always ready to reveal new layers of mystery and wonder. Now, let's unravel a concept that feels like it's straight out of science fiction: cosmic strings. Imagine the early universe as a chaotic, seething cauldron of energy, cooling rapidly as it expands. In this turbulent environment, tiny imperfections could have formed like cracks in ice as it freezes. These imperfections, if they exist, would be cosmic strings, one-dimensional defects in the fabric of space-time, relics from the universe's infancy. But what exactly are cosmic strings, and how could they influence the stretching of the cosmic fabric we observe today? Cosmic strings are thought to be incredibly thin but extraordinarily dense, stretching across vast distances in the universe. Picture them as cosmic threads, thinner than an atom but potentially millions of light years long, carrying immense amounts of energy. These structures aren't made of matter or particles in the traditional sense. They're more like ripples in space-time itself, left over from a time when the universe was still taking shape. If they exist, they would be among the oldest and most mysterious objects in the cosmos, offering a glimpse into the universe's earliest moments. But how do cosmic strings form? To understand this, we need to revisit the early universe, a time when fundamental forces and particles were still coming into existence. As the universe cooled, it underwent a series of phase transitions, much like water turning into ice. During these transitions, the symmetry of the universe could have broken in uneven ways, creating defects in space-time. These defects would manifest as cosmic strings, stretching across the cosmos like scars from the universe's birth. It's a bit like watching a pot of water boil. When the bubbles form and pop, they leave behind ripples and patterns. Cosmic strings could be the universe's version of those ripples, frozen in time. One of the most intriguing aspects of cosmic strings is their potential influence on cosmic expansion. While they're incredibly thin, their immense energy could create gravitational effects, warping space-time around them. This warping might contribute to the stretching of the cosmic fabric, subtly shaping the way galaxies and clusters form. Some theories even suggest that cosmic strings could act as gravitational lenses, bending light from distant objects and creating telltale patterns that astronomers could detect. These patterns would be like fingerprints, offering clues about the presence and behavior of cosmic strings. But here's the challenge: cosmic strings are incredibly hard to detect. Unlike black holes or neutron stars, they don't emit light or radiation in ways we can easily observe. Instead, scientists have to look for indirect evidence, such as distortions in the cosmic microwave background or unusual gravitational lensing effects. These subtle signals could hint at the presence of cosmic strings, but so far the evidence remains elusive. Despite decades of searching, no definitive proof of cosmic strings has been found, leaving their existence as one of the great unanswered questions in cosmology. What makes cosmic strings so compelling isn't just their mystery. It's the way they connect the early universe to the cosmos we see today. If they exist, they could provide a window into the universe's first moments, revealing the conditions that shaped its evolution. They could also offer clues about the nature of dark energy, the force driving the universe's accelerated expansion. Could cosmic strings interact with dark energy, influencing how the cosmic fabric stretches? Could they even play a role in the formation of large-scale structures like galaxy clusters? These are questions that keep scientists searching, pushing the boundaries of our understanding. In the end, cosmic strings remind us that the universe is full of surprises, and the answers we seek might lie in the most unexpected places. They challenge us to think beyond the limits of our current knowledge, to imagine a cosmos that's more intricate and interconnected than we've ever realized. And as we continue to explore the possibilities of these cosmic relics, we're not just uncovering the secrets of the universe, we're also discovering new ways to understand the profound interplay between space, time, and the forces that shape them. It's a journey that invites us to keep exploring, keep questioning, and keep marveling at the incredible complexity of the cosmos. What if one of the most fundamental constants in physics, the speed of light, isn't constant at all? For centuries, we've treated the speed of light as an unchanging pillar of reality, a universal speed limit etched into the laws of physics. But what if that pillar is more like a sliding scale, shifting over time? This bold idea, known as the variable speed of light theory, challenges everything we thought we knew about the cosmos, and if true, it could completely reshape our understanding of cosmic expansion, offering a fresh perspective on why the universe stretches the way it does. Let's start with the basics. In Einstein's theory of relativity, the speed of light in a vacuum, about 300 million meters per second, is considered a fixed constant, symbolized by the letter C. This speed isn't just a number, it's the backbone of physics, tying together space and time into the fabric of spacetime. It's the reason why nothing can travel faster than light, and it's the foundation of equations like E equals mc2, which define the relationship between energy and matter. But what if this constant isn't so constant after all? What if the speed of light has changed over the history of the universe? The idea of a variable speed of light might sound radical, but it's not without precedent. In the late 1990s, physicist João Maguijo and his colleague Andreas Albrecht proposed this theory as a potential solution to some of cosmology's biggest puzzles, including the horizon problem we discussed earlier. If the speed of light was faster in the early universe, they argued, it could explain why distant regions of the cosmos appear so uniform. Light would have had more time to travel and even out temperature differences, creating the smooth, consistent universe we observe today. It's like rewinding the cosmic clock and imagining a time when the rules of physics were slightly different. But how does this connect to the stretching of the cosmic fabric? If the speed of light has varied over time, it could have profound implications for how we understand expansion. For one, it might alter the way we interpret the redshift of distant galaxies, the phenomenon where light from faraway objects appears stretched, shifting toward the red end of the spectrum. Redshift is a key piece of evidence for cosmic expansion. But if the speed of light was different in the past, our calculations about how fast the universe is stretching might need to be revised. It's as if the cosmic ruler we've been using to measure distances and speeds has been changing all along, throwing our measurements into question. Another intriguing possibility is that a variable speed of light could interact with dark energy, the mysterious force driving the universe's accelerated expansion. If the speed of light was once faster, it might have influenced the rate at which space itself stretched, potentially altering the balance between dark energy and gravity. Imagine dark energy as a cosmic engine pushing the universe outward, while gravity acts as a brake pulling everything back. if the speed of light changes, it's like adjusting the engine's power or the brake's resistance, reshaping the dynamics of cosmic expansion. Of course, the variable speed of light theory isn't without its challenges. For one, it's incredibly difficult to test. The speed of light is so deeply embedded in the laws of physics that changing it would require rewriting many of the equations we use to describe the universe. And while some observations, like the cosmic microwave background, seem to align with the idea, others remain inconclusive. Critics argue that the theory might be too flexible, offering explanations for almost any observation without making specific, testable predictions. This has led to heated debates within the scientific community, with some calling for more evidence before embracing such a radical idea. Yet, despite these challenges, the variable speed of light theory continues to captivate physicists. It pushes us to question the very foundations of our understanding, to imagine a universe where the rules aren't set in stone but evolve over time. It's a reminder that science is a living, breathing process, always ready to challenge its own assumptions and explore new possibilities. What makes this idea so compelling isn't just its potential to explain cosmic expansion, it's the way it reshapes our perspective on reality. If the speed of light isn't constant, then what else might be up for grabs? Could other constants, like the gravitational constant or the charge of an electron, also vary? These questions open up a universe of possibilities, challenging us to see the cosmos not as a static, unchanging entity, but as a dynamic, evolving system full of surprises. As we explore the implications of a variable speed of light, we're reminded that the universe is far stranger and more wondrous than we've ever imagined. It's a journey that invites us to keep asking questions, to keep pushing the boundaries of what we think we know, and to keep marveling at the incredible complexity of the cosmos. And in that search, we might just uncover a new way to understand the stretching of the cosmic fabric, one that changes not just our view of the universe, but our place within it. What if gravity, the force that holds galaxies together and guides the motion of planets, isn't a fundamental force at all? What if it's more like an illusion, an emergent property of something far deeper and more complex? This is the heart of emergent gravity, a theory that flips our understanding of gravity on its head. Instead of seeing gravity as a force that acts across space, emergent gravity suggests that space-time itself behaves like a fluid, with its properties arising from microscopic structures we can't yet fully see. But how does this idea connect to the stretching of the cosmic fabric, and what could it mean for our understanding of the universe? Let's dive in. To grasp emergent gravity, let's start with a simple analogy. Think of space-time as a vast ocean. On the surface, you see waves, currents, and ripples phenomena that seem to have a life of their own. But beneath the surface, these movements are driven by countless interactions between water molecules, too small and numerous to track individually. In the same way, emergent gravity proposes that the fabric of space-time isn't smooth and continuous, but is instead built from tiny, underlying structures. These structures, whatever they may be, give rise to the macroscopic properties we observe, like gravity and the curvature of space-time. It's as if gravity isn't a force in its own right, but a side effect of something much more fundamental. This idea has profound implications for how we understand cosmic expansion. If space-time is like a fluid, then the stretching of the cosmic fabric might not be driven by forces acting on it from the outside. Instead, it could be an intrinsic property of the fluid itself, a natural consequence of its microscopic dynamics. Imagine pouring water into a container and watching it spread out to fill the space. In a similar way, the universe might be expanding because the fluid-like nature of space-time allows it to flow and stretch, reshaping itself over time. This perspective offers a fresh way to think about dark energy, the mysterious force accelerating cosmic expansion. Could dark energy be a kind of pressure or tension within the fluid of space-time, pushing it to stretch faster and faster? It's a tantalizing possibility, one that challenges us to rethink the very nature of gravity and space. One of the most intriguing aspects of emergent gravity is how it ties into the concept of entropy, the measure of disorder in a system. In the fluid analogy, entropy plays a key role in shaping the behavior of the system. As entropy increases, the fluid becomes more disordered, spreading out and redistributing its energy. Similarly, in emergent gravity, entropy might drive the evolution of space-time, influencing how it stretches and curves. This connection between gravity and entropy isn't just theoretical. It's supported by mathematical models that show how the laws of gravity can emerge from the principles of thermodynamics. It's as if the universe is running on a kind of cosmic engine, with entropy and gravity working together to shape its structure and evolution. But here's the challenge. If space-time is a fluid, what are the microscopic structures that make it up? What's the water in this cosmic ocean? Some theories suggest that these structures could be related to quantum information, tiny bits of data that encode the state of the universe. Others propose that they might involve exotic particles or fields we haven't yet discovered. Whatever they are, their existence would fundamentally change our understanding of reality, revealing a universe that's far more interconnected and dynamic than we've ever imagined. Emergent gravity also offers a potential solution to one of the biggest puzzles in modern physics, the incompatibility between general relativity and quantum mechanics. While general relativity describes the large-scale structure of the cosmos, quantum mechanics governs the behavior of particles at the smallest scales. These two theories have long been at odds, but emergent gravity suggests that they might not be separate at all. Instead, gravity could emerge from the same quantum processes that govern the microscopic world, providing a unified framework that bridges the gap between the very large and the very small. It's a vision of the universe where everything is connected, from the tiniest particles to the vast expanse of galaxies. As we explore the implications of emergent gravity, we're reminded that the universe is full of mysteries waiting to be uncovered. This theory challenges us to see gravity not as a force but as a phenomenon, an emergent property of a deeper, more complex reality. It invites us to imagine a cosmos where space-time flows like a fluid, where entropy shapes the fabric of reality, and where the answers we seek might lie in the microscopic structures we can't yet see. And as we continue to probe these ideas, we're not just learning about the universe, we're discovering new ways to understand the profound interplay between space, time, and the forces that shape them. It's a journey that invites us to keep exploring, keep questioning, and keep marveling at the incredible complexity of the cosmos. What if the universe we call home isn't the only one out there? What if it's just one of many nested inside something far stranger, a black hole? This is the wild and fascinating idea at the heart of black hole cosmology, a theory that suggests our universe might exist within the depths of a black hole, with cosmic expansion driven by the black hole's own unique properties. It's a concept that turns our understanding of reality inside out, challenging us to rethink not just the nature of the cosmos, but also the very fabric of space and time. So let's venture into this mind-bending possibility and explore what it could mean for the stretching of the cosmic fabric. To understand this theory, we need to start with black holes themselves. These enigmatic objects are regions of space where gravity is so intense that nothing, not even light, can escape their pull. They're often thought of as cosmic vacuum cleaners, sucking in everything that comes too close. But what if black holes aren't just endpoints? What if they're gateways to something entirely different? Some scientists propose that inside a black hole, beyond the event horizon, the point of no return, the laws of physics might give way to an entirely new reality. In this view, the crushing singularity at a black hole's core could be the birthplace of a new universe, one that expands and evolves just like our own. Here's where things get truly intriguing. If our universe exists inside a black hole, then the stretching of the cosmic fabric, the expansion we observe, might be tied to the black hole's own properties. Imagine the black hole as a kind of cosmic seed, with its immense gravitational pull shaping the growth of the universe within it. As matter falls into the black hole, it could create a kind of pressure, driving the expansion of space itself. It's like blowing air into a balloon, except in this case, the balloon is the universe, and the air is the energy and matter flowing into the black hole. This idea offers a radical new perspective on cosmic expansion, suggesting that the stretching of space might not be driven by dark energy or quantum fluctuations, but by the gravitational forces of the black hole itself. But how could this even work? One possibility lies in the strange behavior of spacetime near a black hole. As matter falls inward, time slows down dramatically due to the intense gravitational field. From the perspective of someone outside the black hole, time inside would appear to stretch infinitely, creating a kind of frozen moment. But from the inside, time would flow normally, allowing the universe within to evolve and expand. This creates a fascinating paradox. While the outside observer sees the black hole as a static, unchanging object, the universe inside could be teeming with life, stars and galaxies, all stretching and growing over time. This theory also raises profound questions about the nature of black holes and their role in the cosmos. If our universe exists within a black hole, could there be other universes nested inside other black holes? Could this be part of an infinite chain, with each black hole containing a new universe and each universe containing its own black holes? It's a dizzying thought, one that challenges us to imagine a cosmos far more interconnected and layered than we've ever realized. And if this is true, then the stretching of the cosmic fabric might not be an isolated phenomenon. It could be part of a much larger, infinitely complex system. Of course, black hole cosmology isn't without its challenges. For one, we have no direct way to observe what happens inside a black hole, let alone whether it contains a universe. The extreme conditions near a singularity make it nearly impossible to test these ideas with current technology. Yet, despite these hurdles, the theory continues to inspire and provoke, pushing scientists to explore new ways of thinking about the universe and its origins. It's a reminder that even the most outlandish ideas can spark new discoveries, challenging us to see the cosmos in a different light. What makes black hole cosmology so compelling is the way it blurs the line between the very large and the very small, the known and the unknown. It invites us to imagine a universe that's not just expanding, but nested, layered, and endlessly interconnected. And as we ponder the possibilities, we're reminded that the cosmos is full of surprises, always ready to reveal new mysteries and reshape our understanding of reality. Whether or not our universe truly exists within a black hole, the idea itself is a testament to the boundless curiosity and creativity of the human mind, a reminder that the quest to understand the cosmos is as infinite as the universe itself. What if the forces we know, gravity, electromagnetism, and the strong and weak nuclear forces aren't the whole story? What if there's something else, an invisible hand quietly shaping the cosmos in ways we've yet to fully grasp? This is the tantalizing idea behind the search for a fifth fundamental force, a mysterious influence that could be subtly altering the behavior of the universe. While the four known forces govern everything from the orbits of planets to the binding of atoms, this potential fifth force could offer a new explanation for one of the greatest mysteries in cosmology: why the universe is stretching faster than expected. The concept of a fifth force isn't entirely new. For decades, scientists have speculated about the existence of unknown interactions that might exist beyond the scope of our current understanding. These ideas often emerge when observations don't quite align with predictions, like the way distant galaxies are accelerating away from us at speeds that defy the pull of gravity. Dark energy, as we've discussed, is one explanation, but what if there's more to it? Could an entirely new force be at work, one that's been hiding in plain sight, subtly influencing the expansion of the universe? One of the most intriguing possibilities is that this fifth force could interact with dark matter, the invisible substance that makes up a significant portion of the cosmos. While dark matter is thought to be influenced primarily by gravity, a fifth force might introduce additional interactions, altering how dark matter clumps together and shapes the large-scale structure of the universe. Imagine dark matter as a cosmic sculptor, molding galaxies and clusters with its gravitational pull. Now add a fifth force into the mix, and suddenly the sculpture takes on new, unexpected forms. This force could act as a kind of cosmic glue, binding dark matter in ways that gravity alone can't explain, or even pushing it apart, creating voids and filaments on scales we've never seen before. But how do we begin to search for something we can't directly observe? The hunt for a fifth force often starts in the lab, where scientists use incredibly precise experiments to detect tiny deviations from the behavior predicted by the known forces. For example, some experiments examine the behavior of subatomic particles, looking for signs of an extra force that might cause them to interact in unexpected ways. Others study the motion of galaxies and galaxy clusters, searching for anomalies that could hint at the presence of an unseen influence. It's like trying to hear a faint whisper in a crowded room, challenging but not impossible. One particularly fascinating idea is that a fifth force might be linked to the properties of space itself. Just as dark energy is thought to permeate the vacuum of space, exerting a kind of pressure that drives cosmic expansion, a fifth force could be embedded in the very fabric of spacetime. This force might not act uniformly. Instead, it could vary depending on the environment, becoming stronger or weaker in different regions of the universe. In this view, the stretching of the cosmic fabric might not just be a result of dark energy or gravity. It could also be shaped by the subtle, ever-changing influence of this mysterious fifth force. Of course, the search for a fifth force is still in its early stages, and many questions remain. What kind of particles or fields could carry this force? How does it interact with the known forces, and why have we not detected it before? Some theories suggest that this force might be extremely weak, only noticeable over vast cosmic distances. Others propose that it could operate on scales so small or so large that our current instruments simply aren't equipped to detect it. Whatever the case, the possibility of a fifth force challenges us to rethink our understanding of the universe, pushing the boundaries of what we thought was possible. What makes this quest so exciting is the way it opens up new avenues for discovery. If a fifth force exists, it could revolutionize our understanding of everything from particle physics to cosmology, offering fresh insights into the nature of dark matter, dark energy, and the fundamental structure of reality. It's a reminder that the universe is full of surprises, always ready to reveal new layers of complexity and wonder. And as we continue to explore this idea, we're not just searching for a new force, we're uncovering new ways to understand the cosmos and our place within it. In the end, the search for a fifth force is more than just a scientific endeavor. It's a journey into the unknown, a testament to the human spirit of curiosity and exploration. It invites us to imagine a universe that's richer, more dynamic, and more interconnected than we've ever realized. And whether or not we find this elusive force, the pursuit itself reminds us that the cosmos is full of mysteries waiting to be uncovered, each one offering a new perspective on the incredible complexity of the universe. Let's shift our gaze to a faint glow that permeates the entire cosmos, a whisper from the dawn of time itself. This is the cosmic microwave background, or CMB, often called the afterglow of the Big Bang. It's the oldest light in the universe, a relic from a time when the cosmos was just a hot, dense soup of particles and energy. But this ancient light isn't just a snapshot of the universe's infancy, it's also a treasure trove of clues about how the cosmic fabric has stretched and evolved over billions of years. Imagine the universe as it was nearly 14 billion years ago, just a few 100,000 years after the Big Bang. At this point, it was so hot and dense that light couldn't travel freely. It was constantly scattered by free electrons, like a foggy day where you can't see more than a few feet ahead. But as the universe expanded and cooled, electrons combined with protons to form neutral atoms, allowing light to finally break free. This moment, known as recombination, marked the birth of the CMB. The light released during this epoch has been traveling through space ever since, stretched and cooled by the expansion of the universe until it reaches us today as a faint microwave signal. What makes the CMB so extraordinary is the wealth of information it carries. It's like a cosmic fingerprint, imprinted with the patterns of temperature fluctuations that existed in the early universe. These fluctuations, tiny variations in density and temperature, are the seeds of everything we see today: galaxies, clusters, and the vast cosmic web. But they also tell us something profound about the stretching of the cosmic fabric. As the universe expanded, these fluctuations were stretched along with it, leaving behind a record of how space itself has grown over time. One of the most striking features of the CMB is its remarkable uniformity. No matter where you look in the sky, the temperature of the CMB is almost exactly the same, about 2.7 degrees above absolute zero. But within this uniformity, there are subtle differences, tiny ripples that reveal the early universe's structure. These ripples are like echoes of the quantum fluctuations we discussed earlier, magnified by cosmic inflation and stretched across the sky. By studying these patterns, scientists can piece together the history of the universe's expansion, tracing how the cosmic fabric has stretched and shaped the cosmos over billions of years. The CMB also provides critical evidence for the existence of dark energy, the mysterious force driving the universe's accelerated expansion. By measuring the size and distribution of the temperature fluctuations, scientists can determine the geometry of the universe and how its expansion has changed over time. These measurements align perfectly with the idea that dark energy is pushing galaxies apart, stretching the cosmic fabric faster and faster. It's as if the CMB is a cosmic time capsule, preserving the story of the universe's growth from its earliest moments to the present day. But the CMB isn't just a tool for understanding the past, it also offers hints about the universe's future. By analyzing the patterns in this ancient light, scientists can make predictions about how the cosmic fabric will continue to stretch. Will dark energy keep accelerating the expansion indefinitely? Or could something else, like a change in the nature of dark energy or the emergence of a new force, alter the universe's trajectory? These are questions that the CMB helps us explore, offering a window into both the origins and the ultimate fate of the cosmos. What makes the CMB so captivating is the way it connects us to the universe's earliest moments. It's a reminder that the light we see today began its journey billions of years ago, carrying with it the story of how the cosmos came to be. By studying this ancient glow, we're not just uncovering the secrets of the universe's expansion, we're also discovering our place within a vast, dynamic, and ever-evolving cosmos. It's a journey that invites us to keep exploring, keep questioning, and keep marveling at the incredible complexity of the universe. And as we continue to decode the messages hidden in the CMB, we're reminded that the answers we seek are written in the light of the stars, waiting for us to read them. Now, let's turn to a concept that bridges the gap between the cosmos and us, the idea that the universe might be tailor-made for life. This is the essence of the Anthropic Principle, a thought-provoking notion that suggests the universe's fundamental properties, including its expansion, are finely tuned to allow life to exist. But what does it mean for the cosmos to be fine-tuned? And how does this idea connect to the stretching of the cosmic fabric we've been exploring? Let's dive into this fascinating intersection of physics, philosophy, and the profound question of why we're here. To understand the Anthropic Principle, let's start with a simple observation. The universe seems oddly suited for life. Consider the constants of nature, like the strength of gravity or the charge of an electron. If these values were even slightly different, the cosmos as we know it wouldn't exist. Stars wouldn't form, atoms wouldn't bond, and life as we understand it would be impossible. It's as if the universe's settings were dialed in with incredible precision, creating just the right conditions for galaxies, planets, and ultimately, us. This apparent fine-tuning has led some to wonder, is it mere coincidence or is there something deeper at play? The Anthropic Principle offers a way to think about this mystery. In its simplest form, it suggests that the universe must be compatible with the existence of observers, like us, because we're here to observe it. It's not so much an explanation as a lens through which to view the cosmos. But when we apply this lens to cosmic expansion, things get even more intriguing. The rate at which the universe stretches, the balance between dark energy and gravity, and even the distribution of matter, all of these factors seem to align in ways that make life possible. If the universe expanded too quickly, matter would scatter too thinly for galaxies to form. If it expanded too slowly, gravity would pull everything back into a cosmic collapse long before life could arise. It's a delicate balance, one that raises profound questions about the nature of our existence. One way to approach this idea is through the so-called weak Anthropic Principle, which focuses on the idea that we observe the universe we do because it's the only one capable of supporting life. In this view, the fine-tuning of cosmic expansion isn't evidence of design or purpose, it's simply a reflection of the fact that we're here to notice it. Imagine a vast forest with countless trees, each representing a possible universe with different physical constants. We exist in the one tree where the conditions are just right, even if that tree is one among billions. It's a humbling perspective, one that emphasizes the role of chance in shaping the cosmos. But there's also a strong anthropic principle, which takes things a step further. This version suggests that the universe must have properties that allow life to emerge, implying a kind of cosmic inevitability. Some interpretations even propose that the existence of observers is a fundamental requirement for the universe itself. In this view, the fine-tuning of expansion and other cosmic properties isn't just a lucky break. It's a necessary feature of reality. While this idea is more speculative, it opens up fascinating possibilities, from the idea of a multiverse to the notion that consciousness itself might play a role in shaping the cosmos. So, how does all of this connect to the stretching of the cosmic fabric? If the universe is fine-tuned for life, then its expansion must follow a precise trajectory, one that allows galaxies to form, stars to shine, and planets to host life. Dark energy, for example, plays a crucial role in this balance. If it were stronger, the universe would stretch too quickly for structures to form. If it were weaker, gravity might dominate, leading to a premature collapse. The fact that dark energy exists in just the right amount to allow life to flourish is one of the most striking examples of cosmic fine-tuning. It's as if the universe has been calibrated to create the conditions for existence with every parameter, from the largest scales of expansion to the smallest constants of physics working in harmony. This idea also raises profound questions about our place in the cosmos. If the universe is fine-tuned for life, does that mean we're special? Or is it simply a matter of probability with countless other universes, or regions of our own universe existing where life never arises? These questions touch on everything from philosophy to theology, challenging us to think deeply about the nature of reality and our role within it. And while the Anthropic Principle doesn't provide all the answers, it offers a powerful framework for exploring these mysteries. What makes the Anthropic Principle so compelling is the way it connects the vastness of the cosmos to the intimate reality of our existence. It reminds us that the universe isn't just a collection of stars and galaxies, it's a stage, finely tuned and meticulously set, where life can emerge and thrive. As we continue to explore the stretching of the cosmic fabric, we're not just uncovering the secrets of the universe, we're also discovering new ways to understand our place within it. It's a journey that invites us to marvel at the elegance and complexity of the cosmos, and to reflect on the profound question of why we're here to witness it all. What if everything we see, the stars, the galaxies, the very fabric of space-time, isn't real? What if our universe, with all its complexities and mysteries, is nothing more than an elaborate simulation, a cosmic video game running on some unimaginably advanced computer? This is the simulated universe hypothesis, a thought-provoking idea that has sparked debates among scientists, philosophers, and futurists alike. But if our reality is a simulation, what does that mean for the stretching of the cosmic fabric? Could the expansion of the universe be nothing more than a programmed feature, a line of code in the grand algorithm of existence? Let's explore this mind-bending possibility and its implications for how we understand the cosmos. The idea of a simulated universe isn't as far-fetched as it might sound. Think about the rapid advancement of technology in our own world. Video games and virtual reality have become so sophisticated that they can create immersive, lifelike experiences. Now imagine a civilization far more advanced than ours, with computing power beyond our wildest dreams. Could they create a simulation so detailed, so comprehensive, that it replicates an entire universe complete with galaxies, black holes, and conscious beings like us? Some theorists argue that if such a civilization exists, it's not only possible but likely that we're living in one of their simulations. Now, let's connect this to the stretching of the cosmic fabric. If the universe is a simulation, then the expansion we observe, the galaxies racing apart, the space stretching between them, might not be a natural process at all. Instead, it could be a deliberate feature programmed into the simulation to mimic the behavior of a real universe. Imagine a game designer creating a virtual world and deciding how fast it should expand, how quickly galaxies should drift apart. In this view, dark energy, the mysterious force driving cosmic acceleration, might not be a fundamental property of the universe. It could simply be a parameter in the code, a variable tweaked to create the illusion of an expanding cosmos. But how could we ever know if we're living in a simulation? Some scientists have proposed ways to test this idea. One approach is to look for glitches in the simulation, tiny inconsistencies or errors in the laws of physics that might reveal the underlying code. For example, if space-time is pixelated at the smallest scales, like a digital image, we might be able to detect this granularity through high-energy experiments. Another idea is to search for computational limits in the universe, such as the maximum amount of information that can be processed in a given region of space. If we find evidence of such limits, it could hint at the existence of a cosmic computer running the simulation. Of course, the simulated universe hypothesis is highly speculative, and not everyone is convinced. Critics argue that it's impossible to prove or disprove, making it more of a philosophical thought experiment than a scientific theory. Yet, the idea continues to captivate the imagination, challenging us to rethink the nature of reality itself. If the universe is a simulation, then everything we've discovered about cosmology, from the Big Bang to dark energy, might be part of a grand design, a story written by creators we'll never see. What makes this idea so fascinating is the way it blurs the line between science and philosophy. It forces us to ask profound questions about existence, consciousness, and the nature of reality. Are we the players in this cosmic game, or merely characters programmed to believe we're real? And if the universe is a simulation, what lies beyond it, another layer of reality, or something even more unimaginable? These questions don't just challenge our understanding of the cosmos, they challenge our understanding of ourselves. Whether or not the simulated universe hypothesis holds water, it offers a fresh perspective on the mysteries of cosmic expansion. It reminds us that the universe is full of surprises, and the answers we seek might lie in places we've never thought to look. And as we continue to explore these ideas, we're not just uncovering the secrets of the cosmos, we're also discovering new ways to think about the very nature of existence. It's a journey that invites us to keep questioning, keep exploring, and keep marveling at the incredible complexity of the universe, real or simulated. Now let's dive into a phenomenon that bends not just space but time itself, time dilation. This mind-bending effect, predicted by Einstein's theory of relativity, tells us that time doesn't tick at the same rate for everyone. Depending on how fast you're moving or how deep you are in a gravitational field, time can speed up or slow down. But what does this mean for the expansion of the universe? Could the stretching of the cosmic fabric also stretch our perception of time itself? Let's unravel this intriguing connection between time dilation and cosmic expansion. To understand how time dilation plays into the big picture, we need to revisit one of relativity's core ideas. Time and space are not separate entities but deeply intertwined, forming a single fabric called spacetime. Just as space can stretch and warp, so can time. Imagine you're watching a distant galaxy recede from us at an incredible speed. Because of the universe's expansion, that galaxy is moving away faster and faster, approaching the speed of light. According to relativity, as objects approach such extreme velocities, time for them slows down relative to us. This means that while billions of years might pass for us here on Earth, far fewer years could pass for an observer in that distant galaxy. It's as if the universe is playing a cosmic game of time zone roulette, where the rules of time depend on where and how fast you're moving. But here's where it gets even more fascinating. Time dilation isn't just a quirky side effect of cosmic expansion. It could actually influence how we perceive that expansion. When we look at distant galaxies, we're seeing them as they were billions of years ago, thanks to the time it takes light to travel across the universe. But because of time dilation, the clocks in those galaxies are ticking at a different rate than ours. This means that the light we receive from them carries information not just about their distance and motion, but also about how time itself is behaving in their corner of the cosmos. In a way, the universe's expansion isn't just stretching space, it's stretching our understanding of time. This interplay between time and space has profound implications for how we measure the universe's growth. For instance, when astronomers calculate the rate of cosmic expansion using distant supernova or the cosmic microwave background, they're relying on observations that are influenced by time dilation. If we don't account for these relativistic effects, our measurements could be skewed, leading to misunderstandings about how fast the universe is stretching or even the nature of dark energy. It's a reminder that the cosmos doesn't just challenge our understanding of space, it also bends the very fabric of time. What's even more intriguing is how time dilation might shape the future of the universe. As cosmic expansion continues to accelerate, distant galaxies will eventually move away from us so quickly that their light will no longer reach us. But because of time dilation, the clocks in those galaxies will appear to slow down from our perspective, effectively freezing their light in time. It's as if the universe is putting up a cosmic curtain, hiding parts of itself from view while simultaneously stretching the threads of time. This raises fascinating questions about the ultimate fate of the cosmos, not just where it's going, but how we'll perceive its journey. Time dilation isn't just a theoretical curiosity, it's a fundamental aspect of how the universe operates. By exploring its connection to cosmic expansion, we're not just learning about the stretching of space, we're also uncovering how time itself is woven into the fabric of reality. It's a reminder that the universe is far stranger and more interconnected than we often realize, with every observation offering a new perspective on the delicate dance between space, time, and the forces that shape them. And as we continue to probe these mysteries, we're not just uncovering the secrets of the cosmos, we're also discovering new ways to understand our place within it. Now, let's turn our attention to one of the most dramatic phenomena in the cosmos, gravitational waves. These ripples in the fabric of space-time are like cosmic echoes, created by some of the most violent and energetic events in the universe. From colliding black holes to merging neutron stars, gravitational waves carry information across vast distances, offering us a new way to listen to the universe. But these waves aren't just fascinating in their own right. They could also hold the key to understanding how the cosmic fabric stretches and evolves over time. To grasp the significance of gravitational waves, let's start with what they actually are. Picture space-time as a vast, stretchy sheet. When massive objects like black holes or neutron stars move or collide, they create ripples in this sheet, much like a pebble dropped into a pond sends out waves. These ripples are gravitational waves, and they travel through the universe at the speed of light, carrying with them the story of the events that created them. Unlike light or other forms of electromagnetic radiation, gravitational waves pass through matter almost unaffected, giving us a clear, unobstructed view of the universe's most extreme phenomena. What makes gravitational waves so exciting is their potential to reveal secrets about cosmic expansion. When these waves travel across the universe, they're subtly influenced by the stretching of space itself. As the universe expands, the wavelengths of gravitational waves stretch along with it, much like a sound wave lowering in pitch as it moves away. By studying these changes, scientists can measure how fast the universe is expanding, providing an entirely new way to test our understanding of dark energy and the forces driving cosmic acceleration. It's like having a cosmic ruler that stretches and shrinks with the universe itself, allowing us to track its growth with unprecedented precision. But gravitational waves don't just tell us about the present, they also offer a glimpse into the past. Because these waves travel so far and are so difficult to distort, they carry pristine information about the events that created them. For example, when two black holes collide, the gravitational waves they produce can reveal details about their masses, spins, and even the environment in which they formed. This information, in turn, helps us piece together the history of cosmic expansion, showing how the universe has stretched and evolved over billions of years. It's as if gravitational waves are cosmic time capsules, preserving the story of the universe's growth in their ripples. One of the most remarkable achievements in modern astronomy was the first direct detection of gravitational waves in 2015. Using incredibly sensitive instruments like LIGO and Virgo, scientists captured the ripples from a pair of colliding black holes over 1 billion light-years away. This discovery not only confirmed a key prediction of Einstein's theory of general relativity, but also opened up a whole new way of observing the universe. Since then, dozens of gravitational wave events have been detected, each one adding to our understanding of the cosmos and its dynamic, ever-changing nature. What's truly groundbreaking about gravitational waves is their ability to complement other methods of studying cosmic expansion. For example, measurements from the cosmic microwave background and observations of distant supernova have given us a detailed picture of how the universe has grown over time. But gravitational waves provide an independent check on these results, offering a fresh perspective that could help resolve some of the lingering mysteries in cosmology. Are there discrepancies in the rate of expansion measured by different methods? Could gravitational waves help explain the tension between these measurements? These are questions that scientists are actively exploring, using gravitational waves as a new tool to probe the universe's deepest secrets. As we continue to detect more gravitational wave events and refine our instruments, we're not just expanding our understanding of the cosmos, we're also opening up new ways to explore the stretching of the cosmic fabric. These ripples in space-time remind us that the universe is alive with motion and energy, constantly reshaping itself in ways we're only beginning to understand. And as we listen to the whispers of these waves, we're uncovering not just the story of the universe's past, but also clues about its future. It's a journey that invites us to keep listening, keep exploring, and keep marveling at the incredible complexity of the cosmos. Now, let's turn our attention to the vast, empty spaces that stretch between galaxies' cosmic voids. These sprawling regions, devoid of stars, planets, or even much dust, might seem like nothing more than empty space. But in reality, they are far from insignificant. Cosmic voids are an essential part of the universe's structure, acting as the silent counterpoints to the bustling clusters of galaxies. And as we'll see, these voids don't just exist, they actively shape the way the universe expands, offering clues about the forces that stretch the cosmic fabric. Picture the universe as a cosmic sponge, with galaxies clustered together like dense bubbles and vast voids stretching between them. These voids can span hundreds of millions of light years, making them some of the largest structures in the cosmos. But despite their emptiness, they're not entirely devoid of matter. Instead, they're filled with a thin, diffuse gas and dark matter, the invisible substance that makes up a significant portion of the universe's mass. It's this subtle presence that allows voids to play a surprisingly active role in cosmic expansion. So, how do cosmic voids contribute to the stretching of the universe? The answer lies in their gravitational influence, or rather, their lack of it. Unlike galaxy clusters, which are packed with matter and exert a strong gravitational pull, voids are regions of low density. This means they don't pull on their surroundings as strongly. Instead, they act like cosmic repellers, pushing matter away as the universe expands. It's as if the voids are creating pockets of negative pressure, driving the expansion of space within and around them. This effect, combined with the pull of dark energy, helps accelerate the stretching of the cosmic fabric, shaping the universe on the largest scales. But cosmic voids aren't just passive players in the universe's expansion, they also reveal clues about the cosmos's structure and history. By studying the distribution and behavior of voids, scientists can piece together the story of how the universe evolved from a nearly uniform soup of matter after the Big Bang to the intricate web of galaxies and voids we see today. These vast, empty regions are like cosmic fossils, preserving the imprint of the universe's early moments and the forces that shaped it. One fascinating aspect of cosmic voids is how they interact with light. When light from distant galaxies passes through a void, it encounters less matter and gravitational pull than it would in denser regions. This causes the light to travel slightly faster through the void, a phenomenon known as the integrated Sachs-Wolfe effect. While the difference is subtle, it leaves a detectable imprint on the cosmic microwave background, the faint afterglow of the Big Bang. By studying these imprints, scientists can map the distribution of voids and learn more about the universe's expansion and the role of dark energy. Cosmic voids also challenge our understanding of gravity and the behavior of matter on the largest scales. In dense regions like galaxy clusters, gravity dominates, pulling matter together and slowing down expansion. But in voids, the rules are different. Here, the lack of dense matter allows dark energy to take the lead, pushing the boundaries of the void outward and accelerating the expansion of space. This interplay between gravity and dark energy, between the full and the empty, is what gives the universe its dynamic, ever-changing structure. What makes cosmic voids so compelling is the way they remind us that emptiness is as much a part of the cosmos as the stars and galaxies we see. They challenge us to think beyond the visible, to consider the spaces between and the forces that shape them. And as we continue to explore these vast, empty regions, we're not just uncovering the secrets of the universe's expansion, we're also gaining new insights into the delicate balance of forces that hold the cosmos together. It's a reminder that even in the void, there's a story to be told, a story that invites us to keep exploring, keep questioning, and keep marveling at the incredible complexity of the universe. Let's take a moment to think about the universe not just as a vast expanse of space, but as a system governed by the same fundamental laws that shape our everyday world. Enter thermodynamics, the science of heat, energy, and their transformations. These laws don't just apply to steam engines or melting ice cubes. They govern the behavior of stars, galaxies, and even the stretching of the cosmic fabric itself. So, how do heat and energy influence the universe's expansion? And what does this mean for the cosmos's ultimate fate? Let's dive into the thermodynamics of the universe and uncover the hidden forces shaping its evolution. At the heart of thermodynamics is a simple yet profound idea. Energy is always in motion, flowing from one place to another, transforming from one form to another. In the context of the universe, this energy flow plays a crucial role in how space expands. Imagine the early universe as a seething cauldron of energy, hotter and denser than anything we can imagine. As it expanded, this energy began to spread out, cooling and condensing into the matter we see today. But even as the universe grew, the laws of thermodynamics ensured that energy was conserved, shaping the way galaxies formed and the cosmic fabric stretched. One of the most striking connections between thermodynamics and cosmic expansion lies in the concept of entropy, the measure of disorder in a system. As the universe expands, entropy increases, much like shuffling a deck of cards makes it more disordered. This rise in entropy isn't just a side effect of expansion, it's a driving force. Think of entropy as a cosmic clock ticking forward as the universe grows. The more space stretches, the more entropy increases, creating a feedback loop that pushes the universe to expand even faster. It's as if the universe is caught in a dance with entropy, each step leading to greater disorder and greater expansion. But what does this mean for the future of the cosmos? If entropy continues to rise as the universe expands, it could lead to a state known as the heat death. In this scenario, the universe would stretch so far that all its energy would become evenly distributed, leaving no room for stars to form or galaxies to grow. It's a chilling thought, a universe that's not just cold and dark but utterly still, with no more energy flows or transformations. And yet, this isn't the only possibility. Some theories suggest that entropy might interact with other forces, like dark energy or quantum fluctuations, creating new pathways for the universe's evolution. Could entropy, in some way, fuel new cycles of cosmic rebirth? The answer remains one of the great mysteries of cosmology. What's truly fascinating about thermodynamics is how it connects the smallest scales of quantum mechanics to the largest scales of the cosmos. From the flickering of particles in the quantum vacuum to the vast expanse of galaxy clusters, energy and heat are the threads that weave the universe together. By studying these connections, we're not just uncovering the secrets of cosmic expansion, we're also gaining new insights into the nature of reality itself. It's a reminder that the universe is more than just a collection of objects in space. It's a dynamic, ever-changing system, shaped by the flow of energy and the march of entropy. As we explore the thermodynamics of the universe, we're invited to see the cosmos in a new light, not just as a static backdrop, but as a living, breathing entity full of motion and transformation. It's a perspective that challenges us to think beyond the limits of our current understanding, to imagine a universe where heat, energy, and entropy are the keys to unlocking its deepest mysteries. And as we continue to probe these ideas, we're reminded that the universe is full of surprises, always ready to reveal new layers of complexity and wonder. Whether we're staring into the heart of a star or tracing the faint glow of the cosmic microwave background, the laws of thermodynamics are there, guiding the way, shaping the story of the cosmos and our place within it. Now, let's step into a realm where the rules of physics seem to defy intuition, a world where particles can be instantaneously connected, no matter how far apart they are. This is the strange and fascinating phenomenon of quantum entanglement, often called spooky action at a distance by none other than Albert Einstein himself. At first glance, it might seem like a quirk of the quantum world confined to the tiniest scales. But what if this spookiness isn't just a small-scale oddity? What if it plays a role in the grandest scales of the cosmos, influencing the very stretching of the cosmic fabric? Let's unravel this intriguing possibility. To understand quantum entanglement, picture two particles, let's say electrons, born together or interacting in such a way that their properties become linked. If you measure one particle's spin, for example, the other particle's spin instantly aligns with it, even if they're light years apart. This connection happens faster than the speed of light, seemingly breaking the rules of relativity. It's as if the particles share a hidden, instantaneous bond, a connection that transcends space and time. Einstein famously found this idea unsettling, calling it spooky. But decades of experiments have confirmed that entanglement is very real. It's one of the most profound and mysterious aspects of quantum mechanics. But how does this phenomenon connect to the expansion of the universe? To explore this, we need to think about the fabric of space-time itself. In the quantum world, particles aren't just isolated entities, they're deeply intertwined with the fabric of the universe. Some scientists propose that entanglement could create a kind of cosmic network, linking distant regions of space in ways we're only beginning to understand. Imagine spacetime as a vast web with entangled particles acting as the threads that hold it together. As the universe stretches, these threads could stretch along with it, subtly influencing how space expands and evolves. One intriguing idea is that entanglement might play a role in the behavior of dark energy, the mysterious force driving the universe's accelerated expansion. If entangled particles are connected across vast distances, their interactions could create a kind of quantum pressure, pushing space apart in ways that mimic the effects of dark energy. It's as if the universe isn't just expanding because of a mysterious force. It's expanding because of the hidden connections woven into its very fabric. This idea is still speculative, but it offers a fresh perspective on one of the biggest mysteries in cosmology. Another possibility is that entanglement could help explain the uniformity of the universe on large scales. Remember the horizon problem we discussed earlier? How did distant regions of the cosmos become so similar if they were never in contact? Entanglement might provide an answer. If particles in these distant regions were once entangled in the early universe, their instant connections could have allowed them to communicate in a way that smoothed out differences, creating the uniform cosmos we see today. It's a bit like two dancers separated by a vast stage but still moving in perfect harmony because they learned the same steps long ago. Of course, quantum entanglement remains a deeply puzzling phenomenon, and its connection to cosmic expansion is still a topic of active research. How exactly do entangled particles influence the stretching of space? Could their connections create ripples or patterns in the cosmic fabric that we haven't yet detected? These are questions that push the boundaries of both quantum mechanics and cosmology, challenging us to think in new ways about the universe's structure and evolution. What makes quantum entanglement so captivating isn't just its scientific implications, it's the way it blurs the line between the smallest and largest scales of the cosmos. It reminds us that the universe is far more interconnected than we often realize, with hidden threads weaving through space and time, binding everything together. And as we continue to explore these connections, we're not just uncovering the secrets of the quantum world, we're also discovering new ways to understand the grand tapestry of the cosmos. It's a journey that invites us to keep questioning, keep exploring, and keep marveling at the incredible complexity of the universe. Now, let's turn our attention to one of the most elusive and enigmatic particles in the universe, neutrinos. These ghostly travelers, so small and nearly massless that they pass through matter like it's not even there, might seem insignificant at first glance. But don't let their subtle nature fool you. Neutrinos could be quietly shaping the cosmos in ways we're only beginning to understand. From their origins in the hearts of stars to their potential influence on cosmic expansion, these particles hold secrets that could redefine our understanding of the universe's evolution. So, what exactly are neutrinos, often called ghost particles? Neutrinos are subatomic particles with no electric charge and almost no mass. They're produced in huge quantities during nuclear reactions, like those in the Sun or during supernova explosions. Yet, despite their abundance, neutrinos are notoriously difficult to detect. They rarely interact with matter, passing through entire planets without leaving a trace. In fact, trillions of neutrinos are streaming through your body right now, completely unnoticed. It's this ghostly behavior that makes them so fascinating and so challenging to study. But here's where it gets really interesting. Neutrinos might be doing more than just drifting through space. They could be influencing the very fabric of the universe itself. As the universe expands, these particles, while nearly massless, still carry energy, and in the grand scheme of things, even a tiny bit of energy can add up. Over billions of years, the collective energy of neutrinos could subtly affect how space stretches, contributing to the overall dynamics of cosmic expansion. It's like a gentle breeze that, over time, shapes the landscape it passes through. One of the most intriguing possibilities is that neutrinos could help explain the behavior of dark energy, the mysterious force driving the universe's accelerated expansion. While dark energy remains a puzzle, some theories suggest that neutrinos might interact with it in ways we don't yet fully understand. For example, as the universe expands and cools, neutrinos could transition into a state that amplifies the effects of dark energy, adding another layer of complexity to the cosmic expansion story. It's a tantalizing idea, one that bridges the gap between the smallest particles and the largest scales of the cosmos. Neutrinos also offer a unique window into the universe's past. Because they travel so freely through matter, they carry information about the environments where they were born. For instance, neutrinos from the early universe, created just moments after the Big Bang, could still be zipping through space today. By studying these ancient particles, scientists can learn about the conditions of the universe in its infancy, shedding light on how cosmic expansion began and how it has evolved over billions of years. It's like uncovering a cosmic time capsule, one that's been hidden in plain sight. What's truly remarkable about neutrinos is their ability to connect the smallest scales of particle physics to the largest scales of cosmology. They remind us that the universe is a deeply interconnected system, where even the tiniest particles can have far-reaching effects. And as we continue to study these ghostly travelers, we're not just uncovering the secrets of their behavior, we're also gaining new insights into the forces that shape the cosmos, from the stretching of space to the mysterious push of dark energy. In the end, neutrinos challenge us to think beyond the visible, to consider the hidden threads that weave through the universe, connecting its past, present, and future. They remind us that even the most elusive particles have a role to play in the grand story of cosmic expansion. And as we continue to explore their mysteries, we're not just learning about the universe, we're discovering new ways to understand our place within it. It's a journey that invites us to keep probing, keep questioning, and keep marveling at the incredible complexity of the cosmos. Now let's peer into the cosmic crystal ball and ask the ultimate question: where is the universe headed? The stretching of the cosmic fabric isn't just a story of the past or the present. It's a tale that stretches into the far future, shaping the destiny of everything we know. As galaxies drift farther apart and dark energy continues to push the boundaries of space, scientists have proposed several compelling scenarios for how this cosmic journey might end. Each one offers a unique perspective on the fate of the universe, from a slow, cold fade to a dramatic, cataclysmic finale. So, what lies ahead for the cosmos? Let's explore the possibilities. First, there's the Big Freeze, also known as the heat death. Picture a universe that keeps expanding faster and faster until galaxies are so far apart that the night sky becomes almost completely dark. Over trillions of years, stars will burn out, black holes will evaporate, and the universe will settle into a state of maximum entropy, a cold, uniform sea of energy where nothing happens. No stars, no planets, no life. It's a quiet, almost poetic end where the universe's energy is spread so thin that it can no longer power the processes that make galaxies, stars, or even atoms. The cosmic fabric will stretch into an endless void, a silent testament to the universe's relentless expansion. But the Big Freeze isn't the only possibility. Some theories suggest a far more dramatic fate, the Big Rip. In this scenario, dark energy doesn't just push galaxies apart. It grows stronger over time, eventually overpowering even the forces that hold atoms together. Imagine a universe where space itself is torn apart, ripping galaxies, stars, planets, and even molecules into shreds. It's a violent, chaotic end where the cosmic fabric isn't just stretched, it's ripped to pieces. While this might sound like the plot of a sci-fi movie, it's a real possibility if dark energy behaves in a certain way. The Big Rip would mark the ultimate triumph of expansion, a universe torn asunder by its own relentless stretching. Then there's the Big Crunch, a scenario that flips the script on cosmic expansion. Instead of stretching forever, the universe could one day reverse course, collapsing back in on itself. Picture the cosmic fabric not as an endlessly expanding balloon, but as a rubber band that's been stretched too far and begins to snap back. In this scenario, gravity eventually overcomes dark energy, pulling galaxies, stars, and planets back together in a fiery, chaotic collapse. The universe would end not with a whisper, but with a bang, a cosmic reset that could potentially spark a new Big Bang and the birth of a new universe. It's a cyclical vision of the cosmos where expansion and contraction are part of an eternal rhythm. These scenarios aren't just speculative, they're grounded in the physics of cosmic expansion and the behavior of dark energy. The Big Freeze assumes that dark energy remains constant, steadily pushing the universe apart. The Big Rip suggests that dark energy could grow stronger over time, becoming a runaway force that tears the cosmos apart. And the Big Crunch hinges on the idea that gravity could one day reclaim its dominance, reversing the expansion and bringing everything back together. Each scenario paints a different picture of the universe's ultimate fate, shaped by the delicate balance between dark energy, gravity, and the stretching of the cosmic fabric. But here's the twist: we don't yet know which of these futures, if any, will come to pass. The universe is full of surprises, and our understanding of dark energy and cosmic expansion is still evolving. Could there be other possibilities we haven't even imagined? Could the universe end in a way that defies all our predictions? These are questions that keep scientists awake at night, driving them to explore new theories and gather more data. What makes these scenarios so compelling isn't just their dramatic implications, it's the way they challenge us to think about the universe as a dynamic, ever-changing system. They remind us that the cosmos isn't static, it's a story still being written, with each chapter shaped by the forces that stretch and shape the cosmic fabric. And as we continue to unravel these mysteries, we're not just learning about the universe's future, we're also discovering new ways to understand its past and present. In the end, the fate of the universe is a reminder of how much we still have to learn. Whether it's a slow fade, a violent tear, or a fiery collapse, the journey of cosmic expansion is a testament to the beauty and complexity of the cosmos. And as we explore these possibilities, we're reminded that the universe is full of surprises, always ready to challenge our assumptions and inspire our curiosity. So, as we look to the future, let's keep asking questions, keep exploring, and keep marveling at the incredible story of the cosmic fabric, a story that's still unfolding one stretch at a time. As we've journeyed through the science of cosmic expansion, from dark energy and quantum fluctuations to the potential fates of the universe, it's impossible to ignore the deeper questions that linger beneath the surface. What does it mean for us as tiny beings on a pale blue dot to live in a universe that's constantly stretching, evolving, and reshaping itself? Beyond the equations and observations, cosmic expansion invites us to reflect on our place in the grand tapestry of existence, sparking conversations that bridge the gap between science and philosophy. At its core, the idea of an expanding universe challenges our sense of permanence. For much of human history, we've seen the cosmos as a stable backdrop, a timeless stage where the drama of life unfolds. But the discovery that space itself is stretching, that galaxies are racing away from us, shatters that illusion. The universe isn't static, it's dynamic, ever-changing, and indifferent to our presence. This realization can feel humbling, even unsettling. It forces us to confront the fleeting nature of our existence, not just as individuals but as a species. In a cosmos that's growing colder and darker with each passing moment, what does it mean to strive, to create, to dream? Yet, there's also a profound beauty in this perspective. The stretching of the cosmic fabric reminds us that we're part of something far greater than ourselves. The atoms in our bodies were forged in the hearts of stars, scattered across the universe by supernova, and gathered here by the forces of gravity and time. We are, in a very real sense, children of the cosmos, born from the same processes that shaped galaxies and stretched space itself. This connection to the universe isn't just poetic, it's scientific, grounded in the laws of physics and the history of the cosmos. It's a reminder that we're not separate from the universe, but deeply intertwined with its story. Cosmic expansion also raises questions about the nature of existence itself. If the universe is stretching, what does that mean for time, for reality, for the very concept of now? When we look at distant galaxies, we're seeing them as they were billions of years ago, their light just now reaching us. In a sense, we're gazing into the past, watching the universe unfold in slow motion. This strange dance of time and space challenges our intuitive understanding of reality, suggesting that the universe is far more complex and interconnected than we often realize. It invites us to think beyond the here and now, to imagine a cosmos where past, present, and future are woven together in a single, ever-expanding fabric. And then there's the question of meaning. In a universe that's destined to stretch into an endless void, what purpose can we find? For some, the answer lies in the act of exploration itself. The very fact that we can observe, measure, and ponder the mysteries of cosmic expansion is a testament to the resilience and curiosity of the human spirit. We may be small, but our capacity for wonder is boundless. Every discovery, every insight, every moment of awe is a defiance of the cold, indifferent universe, a declaration that, even in the face of cosmic expansion, we can find meaning in the pursuit of knowledge. Others find solace in the idea of connection. As the universe stretches, it also weaves us together, linking us to distant galaxies, ancient stars, and the very fabric of space-time. In a cosmos that's constantly changing, our shared humanity becomes a source of strength and purpose. Whether we're scientists peering through telescopes or simply stargazers marveling at the night sky, we're all part of the same cosmic story, united by our curiosity and our desire to understand the universe and our place within it. Ultimately, the philosophical implications of cosmic expansion remind us that science isn't just about answering questions, it's about asking them. It's about confronting the unknown, embracing the mysteries, and finding wonder in the vastness of the cosmos. The stretching of the cosmic fabric isn't just a scientific phenomenon. It's a mirror reflecting our deepest hopes, fears, and aspirations. It challenges us to think beyond ourselves, to imagine a universe that's both infinite and intimate, and to find meaning in the ever-expanding journey of discovery. And as we continue to explore, to question, and to marvel, we're reminded that the universe isn't just something out there. It's something within us, a part of who we are and who we might become. As we bring this cosmic journey to a close, it's impossible not to feel a sense of awe at the mysteries we've uncovered. The stretching of the cosmic fabric isn't just a scientific puzzle. It's a profound reminder of how much we still have to learn about the universe. From the invisible force of dark energy to the ghostly whispers of quantum fluctuations, we've explored 15 theories that challenge our understanding of reality itself. Each one offers a unique lens through which to view the cosmos, inviting us to rethink not just the universe but our place within it. What's truly remarkable is how these theories, while distinct, are all pieces of the same grand puzzle. Whether we're peering into the quantum realm or gazing at the vast emptiness of cosmic voids, we're uncovering the threads that weave the universe together. It's a tapestry of forces, particles, and phenomena, each one contributing to the story of how the cosmic fabric stretches and evolves. And while we've made incredible strides in understanding this process, the journey is far from over. Every discovery leads to new questions, new mysteries, and new opportunities to explore the unknown. This exploration isn't just about science, it's about curiosity, wonder, and the relentless human drive to understand the world around us. It's about looking up at the night sky and feeling that deep, unshakable connection to something greater. Whether you're a seasoned space enthusiast or someone just beginning to dip their toes into the cosmic ocean, this journey reminds us that the universe is a place of endless fascination waiting to be explored. Thank you for joining us on this adventure through the mysteries of cosmic expansion. If you've enjoyed this deep dive into the wonders of the universe, don't forget to subscribe and share your thoughts in the comments below. Let's keep the conversation going because the cosmos is full of stories yet to be told. Until next time, keep looking up. You never know what wonders might reveal themselves in the